Okay, very good morning, everyone. Welcome to another HSMA training day. So today we've got two different sessions for you. So this morning we're going to be finishing off our discrete event simulation module and looking at object-oriented code and a few little nice little extras that we can do in SimPy as well. And then this afternoon, we're going to begin on one of the largest modules of the training program, the AI machine learning module. And we're going to take some our first tentative steps into the world of AI. Got a really nice gentle introduction to it this afternoon with what I hope will be a very fun group exercise for you to undertake. Certainly people enjoyed it last year. So that's to come up this afternoon. But this morning, we are going to go back to our old friend SimPy, who we met last week, and found that SimPy was actually a really nice way in which we could create discrete event simulation models in Python using the standard framework. So the last bit of the puzzle really is showing you how to do this in an object-oriented way. So I mentioned last week that when I was showing you things, we were using the non-object oriented approach. We were using generator functions, which we still use in the object oriented approach because they're the heart of how SimPy works. But we were passing things all over the place. Okay, we were passing in resources, and we were passing in parameter values to a function, and then that would pass it over to another function. And you probably already got a bit of a glimpse that beyond anything that resembled a fairly simple system, that might get a little bit annoying quite quickly. So the object-oriented approach is actually a far more elegant way of being able to structure our models. And for smaller models, it might look like overkill. But of course, the kind of models that we're showing you here aren't probably the kind of models that you'll be building. You'll be building something a little bit more complex in your projects. And so showing you how you can create these a bit more elegantly, hopefully you'll see how they're much easier to scale up and it makes them much more elegant as well. But before we dip into the object-oriented side of things, what I'm going to suggest we do is first go back to the example from last week. Let's just remind ourselves of the standard SimPy structure, and then we'll see how we can translate that into object-oriented code. So what I'm going to do here, I'm just going to bring up here, this is the very simple example that we had last week, where we've just got a single queue for a single activity with a single resource queuing for a nurse. So basically, remember with SimPy, essentially what we have are lots of generator functions. We've got a generator function here that represents the discrete event simulation generator, the thing that is bringing our entities into being, the kind of entrance point for the model. And into that function basically runs an infinite loop whilst the model runs, and it creates basically instances of the other activity generator, which represents the patient journey. And it keeps doing that, keeps creating instances of this generator function, and then sampling a time and inter-arrival time until it has to do it again. So it represents patients, or whatever our entities are, coming into the model, and then it freezes for the amount of time that it's sampled, and then it does it again. So what we end up with is lots of these generator functions that represent our journeys, in this case patient journeys, throughout our system, and each one kind of represents an individual patient's journey. Within that journey function, we specify basically all of the things that are potentially going to happen to this patient, in this case just one thing, but we basically have we request a resource, in this case a nurse. We freeze in place until that request can be met, and that represents our queue. We can calculate our queuing time from the time at which we asked for the nurse to the time at which we came back to this function, because then a nurse is available. And then we randomly sample an amount of time that we will spend in this activity, and then we freeze in place with the resource, so locking the resource in place as well for that amount of time. And that's basically SimPy. That's how it works. You've got generator functions that represent entities coming into your model, and you've got generator functions that represent the journeys for each of those entities, and we create an instance of each of those journey functions for each patient coming in. So that's what we've seen so far. But what we had to do, as we remind ourselves here, into these generator functions. So for the one that's generating our patients here, we had to pass in the simulation environment, the inter-arrival time, so that it could use that here, the any activity time information, so the mean, so means that we could use to sample from an in this case an exponential distribution, plus any resources. And then this function would use the inter-arrival time and the environment, but then would pass everything else over to this other function. So you're constantly getting parameter values that are being passed from one thing to another. Okay, apologies, sorry, my chair just collapsed. I'm still going. But so you're constantly passing these things from one thing to another. Now that's not very elegant. You can see already it's a little bit messy from one activity, let alone if you've got 30 of them, it would be a mess. So let's talk about a better way in which we could structure this. So basically, here's what we're going to do. We're going to set up a structure in which we have various classes, and each of those classes will represent something about our model. Okay, and the way in which we'll set it up, now there's different ways in which you could do this. The way I've done it is deliberately matching the way in which the official SimPy tutorial works. Now I've done that because there aren't a huge amount of resources out there on SimPy. In fact, our videos from HSMA get tens of thousands of views because there is very little else out there, and some of the stuff that is out there is based on the old version of SimPy. So it's a bit of a minefield if you're trying to learn SimPy code. So the best resource that's out there, other than what we're going through today, is the official SimPy tutorial. So the structure in which I'm showing you today matches the way that they do things. Because then if you want to look at the SimPy tutorial, it'll make sense. Okay. So here's how we're going to do it. We're going to have 3 types of class. We may have more than one of these classes, but we're going to have basically 3 types of class. We're going to have one class that we call class G. And this class is a bit of an odd class because it does 2 things that are slightly different to classes that we've seen so far. First of all, it doesn't start with a capital letter, even though I said classes should always start with a capital letter. This one doesn't. And the reason it doesn't is because unlike in object-oriented programming normally, where you create a class which is a blueprint, and then you create instances of that class which you then work with, which we'll do elsewhere. But for this particular class, we're not going to do that. We're just going to refer to the class itself. We'll never create an instance of it. And sometimes you do this in object-oriented programming where you want to have a kind of class that holds a store of information that you can use anywhere else in your code. So what we're going to use this for, the G stands for our global class. And it's basically going to store all of our global variable values, things that we'll need all across the model. So things like average inter-arrival times, average process times, all that stuff that we were passing across before, how long the model's going to run for, how many runs we want it to run for, that kind of thing. All of those kind of global parameters that we need all over the place. We're going to put those in a class that we call G. It's not going to have any methods. There'll be no methods, and there won't even be a constructor. Well, certainly not one that we specify, because we're never going to create an instance of this class. We're just going to use it basically as a storage area where we can dump all of our stuff, all of our model parameters. Okay, so we call that class G, lowercase g, and we'll store our global parameters there. And then when we want to access them, we won't create an instance of the class. We'll just say g dot mean inter-arrival, or whatever we've called it. Okay, so we can access it anywhere in the model just by saying g dot the thing we need. Okay, then so that helps us quite a lot, because that means we don't have to pass around all that nonsense around. You know, if you've got 30 activities, Well, that's 30 process times that you're going to need. At least there may be more if you've got different types of process time for the same activity. So you don't really want to be shunting that all around the model. So actually just having it all in one place, and then you can just refer to it as you need it, makes much more sense. So that helps us a lot already. Then we're going to have another class which represents our entity. Now, you might have more than one of these classes if you've got more than one type of entity in your model. So far, we've only looked at single entity models where you've got, patients are your entity. But you could have multi-entity models. We mentioned that last week, where you have different types of entity coming in. So you might have different types of patient, or you might have patients as well as telephone calls coming in. We saw a glimpse of that, as well as test results. They are different entity types. So you might have more than one of this type of class. But basically, we'll have a class that for each type of entity. So if we've just got one type of entity in our model, then we'll just have one of these classes. And that will represent our entities that are flowing through. And basically, each of those entities might have some attributes. So last week, we saw an example where we basically had patients, and each of them had a patient ID. That might be an attribute of the patient, some piece of information that the patient carries with them. In real-world systems, you might also have things like age, or probability of going down a particular route for that patient. Things like that, stuff that is unique to that patient, and they can carry that information with them. So they may have some attributes. They might as well have some methods. There might be some methods that you want to put in that class, or they might just have a constructor that sets off these attributes. Depends what you're doing. Okay, but you've got a way of expressing in this case, a patient, or whatever your entity is, as having some information they carry with them and some methods that they can undertake. So the example I'll show you this morning, you'll just have a single entity class, and it'll have some information, patient ID, and it'll just have a constructor method. But you can, of course, include more. Then we have a single class that represents our model. Now, SimPy calls it in the tutorial the model class, which can be a bit misleading because you think, well, the whole thing is the model, really, which it is. The best way to think about this, and actually Mike uses this structure, is to think of this as your real world system that you're modeling. So if you're modeling a GP surgery, this is the class that represents your GP surgery. And in this class, that's going to hold the environment, the SimPy environment in which all of our resources, etc., are going to live. It'll hold the resources as well, so all the different types of resources that we've got for our model. And it'll have all of the methods that we need, which will include all of the journey stuff. So those generator functions that we were generating before, which said, this is a patient's journey through the system, that'll hold those. So if we've got more than one type of journey, we'll have more than one generator function within that method. And we'll also have a constructor that will set all this up. We will have a run function as well, a run method. The run method will basically define what will happen in the model, the series of steps that it'll need to go through when it starts running the model. And we might have other things. And the other thing we'd have is the entity generator or generators, which is we've already seen. These are the things that are bringing our entities into being. So we may only have one, but if we've got more than one entrance to the model, we might have more than one. Okay, so we're splitting it into these three components. We've got a G class where we stuff all of the kind of global stuff that we might need to refer to at any point, just so that we can say G dot inter-arrival time for seeing the nurse, or for coming in for the nurse, etc. And then we've got a class for each type of entity that we've got in our model, and that the attributes in that will represent the information they carry with them, things like ID, age, anything like that, any methods we may want that are unique to patients. And then a kind of model class which represents our system, which will hold the simulation environment and the resources, and so that we don't need to pass those things across because they'll live in the model. And basically four types of at least four types of methods: a constructor, which will set up the model, and one or more entity generators, which will bring our things into being, our entities into being, one or more journey functions, entity journey functions that will describe the processes happening, and a run function, which will basically define how the model runs. You may, of course, have more than that, and we will see examples of that this morning as where you'd add extra methods into that model as well. So let's have a look. Let's have a look at a really simple example. Let's have a look exactly the same example that I showed you a moment ago and that we saw last week, where we just got the simplest possible discrete event simulation model. Single activity, single resource, single queue, single entrance, single sync. Okay, so we've got patients arriving for a weight loss consultation. They queue to see a nurse. They spend an amount of time with a nurse and then they leave. Okay, really simple model. Exactly the same model I just shown you that that we looked at last week. Let's see how we now do that in terms of an object-oriented structure. So the way we're going to set this up, we're going to have a class G, which will store the stuff that we need across the model, our global parameters. So here that'll be our inter-arrival time for people coming in to see the nurse, the average time that they'll spend with the nurse, the number of nurses that we've got, not the nurses themselves, they'll be stored in the model, but the number of nurses, that's a parameter value. How long we want to run the simulation for and how many runs. Okay, so the G class will store all of that. Then in the patient, for our entity class, we've just got one type of entity, a weight loss patient. They'll just have a simple structure where they've just got a single attribute, which is their patient ID. They won't have anything else, and they won't have, the only method they'll have is a constructor. And then we'll have a class that represents our GP surgery. And that will house our simulation environment, our resources, in this case, just a single nurse, or just a nurse resource, might be more than one nurse. And then the methods to construct the GP surgery, to generate new arrivals to the weight loss clinic, to describe that journey through the system and to run it. Okay. Now, before I show you the code, you might think when you're first looking at this seems a lot more complicated than what we saw before, and it is slightly more complicated. I'd say to you two things though. First of all, don't panic. You're going to spend a lot of this morning in a group exercise, quite a long group exercise. And part of the reason it's so long is to allow you to look back through this code together and make sure you get your head around it first before you go and tackle the problem. So you're going to have plenty of chance to have a look at this. So don't worry if this doesn't sink in immediately. The second thing I'd say is that it can seem like overkill, as I mentioned, for a very simple model. But when you then build up more complex models, you'll see that this is a much nicer structure to use. But necessarily, we're starting simple with this. So I'm going to show you the code for doing this. You've been given this code file as well, SimPy 001.py. So let's switch across to Spider, and let's have a look at the code. So we start off in exactly the same way. We import SimPy and we import random. There, when you're doing SimPy modeling, they are the two most common libraries. You'll probably import pandas as well in real-world applications, as you saw last week. Probably CSV as well for reading and writing CSV files. But SimPy and random are core for doing this kind of modeling. So first thing we do, set up our G class, our global variable class. Okay. So this is where we're going to store our global parameters. Remember, we don't create an instance of this, so we don't need a constructor. It's just a holding pen for our parameter values. We're just going to refer to this class directly. Something you should never normally do. But this is the exception that I mentioned when we covered object-oriented programming, this kind of thing. So class G, and I'm going to specify the class, and it's basically just a set of variable assignments. So here I've got my weight loss patient inter-arrival time at 5 time units, it'll be minutes in our model. Our mean consultation time of 6, the number of nurses being 1, the simulation duration of 120 time units, and we'll have 10 runs of the model. So those are our global parameters that we are setting up in our G class. That means that whenever I need to grab the inter-arrival time or how many nurses I've got, I can just refer to class G and grab that information out. So if I want the mean consultation time with a nurse, I just say G dot mean consult, and wherever I am in the model, that will give me that number. Okay, so it makes it much easier. Okay, so that one's nice and easy. Now let's set up our entity class. In this case, we're setting up a class for a weight loss patient. That's the only entity we've got in this particular model. So we set up our class in the normal way. Class, this time we do use a capital letter at the start because we should for the class names. And all we're going to set up here, remember we said we don't want any methods and we're just going to have one attribute. So all we're going to have is a constructor where we pass in a patient ID, and that ID gets allocated to the as the attribute of that patient. Now, in real world system, you could do all sorts of stuff for this. You might want to, set up an age. You might want to set up probabilities of going down certain routes. You might want to set up conditions they have, length of time they've had the condition, number of previous admissions. There's all sorts of information that the patient might carry with them. But just for this, we're just going to have a simple patient ID that we allocate to them, as we've seen before. So all of that, our entire patient class is that, in this case, is just a weight loss patient. This is the constructor, and it just sets up this thing called ID, this attribute called ID that gets passed in. So when we create a new patient, we say this is their ID, and it sets it up. Okay, so that's all this one's going to do. Then we have our class that represents our GP surgery. Okay, so I've called this class GP surgery model, and here I'm going to set up the four main things that we're going to want as a default. So the first thing we need to do is set up the constructor. So the constructor for the model class, we're going to need to set up, remember it's going to store the environment, it's going to store any resources that we need for our model, plus anything else that we might need that's unique to this model. So in this case, we're going to set up a new environment. It's going to be a SimPy environment. Now we set those up before at the sort of the bottom of the code. Here we're doing it when we construct a new GP surgery model. We'll create a new SimPy environment and we'll store it in self.env. So remember, self dot just says it belongs to this class. It belongs to this instance of the class, I should say. So when we create an instance of the GP surgery model, it'll have an attribute called environment or env that will store the SimPy environment. We've also got a patient counter for this particular model, because I'm going to have a patient counter that I'm going to start at 0. So the way I'm going to allocate my patient IDs, much as we saw last week, every patient that comes in, they'll just get the next number. So the first patient will be 0, the next patient will be 1. Again, in the real world, you might have something a bit more advanced for setting up patient IDs, but we're just going to do it like this here for simplicity. And then the other thing I need to set up my resources. Because remember, the resources are going to be stored in the model class. We've only got one type of resource here, which is a nurse. So I set up my nurse much as I did before, except it's going to be stored against the instance of the GP surgery. So I have to put self dot because it's an attribute now of this object. So I call it self.nurse. That's where it'll live. And it's a SimPy resource, just as we saw before. Remember, we need to pass in the environment in which it will live, which is now stored within this model class as an attribute. So we need to say self.env because it lives within this model, the instance of the GP surgery. And then we have to set up the capacity. And previously we were just hard coding this, but now we're going to say, okay, the number of nurses I want, I've actually got that stored in my G class. So remember I said we can put stuff in our G class that we can refer to anywhere in the model. So I set up number of nurses. If I scroll back up to the class G here, I've got number of nurses stored as an attribute, which means I can change that. So if I wanted to change it to 5 nurses, I can just do that in my G class. It makes it very easy to be able to change various parameter values in our model, which you're going to want to do when you're doing what if analysis. You're going to change various values essentially in your model. So here we just say, well, the capacity is whatever the number of nurses is in the G class. Okay, so we just say G dot number of nurses. So that's our constructor. This will set up a SimPy environment that will store as an attribute of the model, stored in env. We'll store a patient counter, which will start at 0. and we'll store a nurse, which will be a SimPy resource, and the number of nurses will be defined in our G class, and we'll refer to that directly there. So we don't need to pass in anything when we set up this GP surgery model, because it will automatically create a SimPy environment. It'll set the counter to 0. So these are the default values, and the number of nurses will be set up as whatever we stored in our G class. Then we need a method that essentially is our generator function for generating new patients coming in. So this is exactly the same as it was before. It's just a couple minor differences because it now lives in a class. So here's my generate weight loss arrivals, the same structure, exactly the same as before. Increment the patient counter, create a new instance, process that, sample the inter-arrival time to the next one, and then freeze. All of that's exactly the same, just with a very slight difference. So because this is a method within a class, we need to pass in self. Remember, that's the copy that represents the instance of this class. Then in our infinite loop here, I'll increment the patient counter. But remember, patient counter is stored as an attribute of this class, this object. So I need to say self dot. So when I create a new GP surgery, I want you to increment your patient counter by 1. We're only going to create 1 instance of it, but nonetheless. Then I'm going to create a new patient. Now, before, what we were doing here was creating a new instance of a generator function. Remember, it was the generator function that defined the journey through the system. Here, we're doing something slightly different. Here, we're creating a new instance of our patient class that we defined up above. So if I scroll up, oops, here, this is what we're going to create a new instance of. One of these, a weight loss patient. And remember, we said a weight loss patient, basically all they have is an ID. But if we had more information in there, we'd said this is where we'd set it up. Okay. But we're going to create a new one of these, and let me scroll back down. And we're going to give them the patient ID as whatever I've incremented. So I've actually incremented first here. So the first patient will be patient 1. So we'll create a new one of those. Then we're going to start the journey function, what we have, the generator function that represents the patient's journey. We're going to start that running. Now that, so we use env.process just as we did before, but remember env is now stored as an instance of this object, so we have to put self.env. And the thing we pass in, the thing we want it to process, the generator function we want it to process, is now stored in this class, because the next method, the attend weight loss clinic, the generator function that will describe that patient journey, is now stored within this class. So we now say self.attend WL clinic, and that will call that function. So it's doing exactly the same as it was before, but we've now stored it in this class. However, there is one slight difference here. Remember up here, before we were creating a new instance of the generator function. Now we're creating a new instance of the patient class. And what we're going to do here instead, we're going to call this generator function that represents the journey, and we're going to pass in the patient. So it's essentially we're saying create a new journey, and here's the patient that's going to go through that journey. So that's what we're doing. Then we sample the inter-arrival time to the next patient, exactly the same structure as before. The only difference is because we're not passing around the inter-arrival time anymore, we're going to grab the mean inter-arrival time just from our G class. Remember, that's stored up there, so we don't have to pass it in. We can just grab it from G. And then again, just as we did before, we'll freeze this generator function that's generating our new patients for however long we sampled. The only difference being that we need to remember to include self dot, because it's going to be stored in the copy of this object instance. So the structure is exactly the same. It's just because it's in an object-oriented framework, we've got a few minor differences. And the key difference really is that we're creating an instance of a patient class rather than an instance of the generator function. And when we call the generator function down here, we're going to pass in the patient that we've just created. This is then the generator function for the patient journey, the one we've just started running up above, and we've passed in a patient to it. So here we define not just self as being something that needs to be passed in, because self has to be passed in to all methods within a class, but we also pass in the patient, a patient object. So this is basically telling Python, when we tell you to run this process where we set up the patient journey for attending the weight loss clinic, I will give you a patient to put through that journey, and that's what I'm doing. But all of the rest of it, again, exactly the same kind of structure as we had before. We'll print the time the patient started queuing, then we'll request a nurse. Again, the nurse, remember, now is stored within this class. So it'll be the copy of the object that we need to grab self.nurse, grab the nurse that lives in this copy of the object, because it's an attribute of this object now. Wait in place until we can have that. Then print the time they finished queuing, exactly as we did before. Remember, patient ID is now stored in the patient. So the patient object that's been passed in, if we say patient.id, that grabs their ID that belongs to that patient. Then we'll randomly sample how long they'll spend with the nurse, just as we did before. Again, the only difference is we can grab the average time, the mean time that we'll pass it into the exponential distribution. We'll grab that from the G class, and then we'll time out for however long. And again, we need to remember to put self.env because it lives in this class. So those two are exactly the same as we saw before, just with a few sort of minor tweaks. Then we've got the run method, which is the fourth method that you'll always have to have. So you may have more than 4 in your model class. You may have more than 1 generator, bring in patients. You may have more than 1 journey, and you might have additional functions, as we'll see later this morning. But you'll always have at least 4, because you'll have a constructor, at least 1 generator that brings in patients or entities, at least 1 generator function that describes what happens to those patients or entities, and a run method. And the run method, just as we had before, this is at the bottom of the code before, this is the thing that's going to start up our various generators. In this case, we've only got 1 patient generator that's bringing in new patients. We're going to start that thing running so it can start bringing patients into our model. And we're then going to tell the simulation to run for the amount of time. So this is exactly as we had it before. The only difference, again, is that we need to say this environment lives in self. So we need to say self.env, and the generator function that's bringing them in lives in this class as well. So we need to say self dot, it lives in this class. And down here where we run the simulation, again, we need to say self.env because it lives in this class. And the simulation duration we store in G. So we grab it from G. We say G dot, the thing we need. So that, all of that basically defines our code, our classes within our model. And here, remember, all we've done above there essentially is just define things to tell Python what to do when we start, when we create instances of them. But now we need to set the thing running, because we've defined a run function, but we haven't called that yet. So here's what we're going to do. We basically, remember, we said if we want more than 1 run of a simulation in SimPy, we put everything in a for loop, including the setup of the simulation. And before, that meant putting quite a bit in that for loop, because you had to do all the setup down at the bottom. But here, because we've got it all in an object-oriented structure, it's much simpler. So here I say for run in range, and then however many runs. Remember, that's stored in G, so I can just grab that. I can grab things in G from anywhere in my model. And then I'm going to print, I'm just going to have a little print message that says run whatever the number is out of however many runs we've got. I'm going to be user friendly here and put run +1 so it doesn't start from run 0. And all I'm going to do, I'm going to create a new instance of the GP surgery model. That's this class up above that contains the patient generator, the patient journey generator function, and the run method, as well as its own constructor. So create one of those. and then set the run, call the run method of that class. So we'll create a new GP surgery and call the run method, which then will start the generator that's going to create our new patients. It'll start that running and then run the simulation for an amount of time. That once it's done that, once it's run for that amount of time, 2 hours in this case, that will represent one run of the simulation, and back around the loop will go. We'll create another GP instance of GP surgery model, and we'll run that. And the nice thing is that means that we could then store each of those instances of GP surgery, the GP surgery model, in something like a list if we wanted to, or a pandas data frame, because remember, we can store objects in iterable objects. So we could then have the actual instance of that run if we wanted to. So if I just run this, let's run that, see what happens. And there we go, and we can see our models run, and we can see our various messages popping up. If I just scroll up a moment, we can see that's run 10 of 10, so it's done this 10 times. In run 10, patient 1 started queuing at 0, they finished queuing at 0 because there's no other patient in there. 2 started queuing at 6, but they finished queuing at 10, they had to wait because the patient 1 was still being seen, etc., etc. So exactly as you saw before, but with this slightly more elegant structure. So don't panic if you haven't understood all that at the moment. Don't worry, you most of this morning you're going to be looking at this before you try doing this yourself, as there'll be plenty of chance in your groups to read through this. But it's not quite as imposing as it first looks. You already know the basic structure, that basic structure of generator functions representing generators that bring in new entities and generators that describe journeys of those entities through a system. That still holds. It's just the way where we put them and the way in which we call them is slightly different, and it makes it more elegant. Just before we move on, any questions about any of that? No? Okay. As I say, don't panic if you haven't understood it all at the moment. This is why you've got a long exercise this morning to read back through this. Now, something else we're gonna mention before you move on to that exercise is storing our results from our trial. So a trial is basically a batch of runs. So if we want to run our model 100 times, we refer to that as a trial. So each individual run of the model would be a run, and then the whole thing would be, that batch would be known as a trial. So if we want to store the results of our trial in our new framework, there's different ways we could do it, but one way is we could do the following. Now, hopefully you saw my message this morning. I've updated these slides just to make it a bit easier for you to follow. So each of these things are numbered, and then I've added into SimPy 002 green comments. Oh, sorry, I shouldn't say green because it could be different. The triple inverted double quotation marks comments that have these numbers, so you can see where we do each of those things, where we add that into the thing we've just seen. Okay, because it seems like a lot of information, and it is. So it's an easier way for you to be able to follow this. So the first thing we're going to do in this example, and again, there's different ways you could do this, we're going to add a run number attribute to the GP surgery model class. So the GP surgery model, before, when we're setting this up before, we had 3 attributes. We had the environment, the SimPy environment. We had a patient counter, which just basically went up from 1 to 2 to 3, etc. And we used that to give patients their ID. And we had an attribute for each of our resources, in this case just a single resource of a resource type of a nurse. We're going to add another one of those in now, and that's going to represent the run number. So the GP surgery model will know which run number it's currently running. So when as it's running its model, it'll know, okay, I'm run 5 of 10. Okay, so let's see how we do that. Let's switch over to the SimPy 002. So you'll see down here, and this will be easier when you look at it yourself. You'll see I've put in these little comments. I've added these in this morning, partly because it made it easier for me to do it without flicking up and down all through the code. But it'll also hopefully make it easier for you to follow where I've added new stuff in, because most of this is exactly what you've just seen. So I just want to show you the new stuff that's been added. So here is where we're going to add in a run number to our GP surgery model. And a run number, something's going to be passed in. So we're going to tell the GP surgery model when we create it in that for loop. When we create a new GP model, we'll say, you are GP model that represents run number 6. Okay. So we'll pass that in. So it needs to be passed into the constructor. And we set that up just as we would any other attribute. We store it self.run number equals run number. So the number I pass in as the run number, store that, remember that, carry that piece of information with you. Okay, so that's fairly straightforward. Then we're also going to add a pandas data frame as another attribute to this model class that will store the various results that we want to capture from each run. So let's have a look back. This is number 2, so we can see that here. So I'm going to create a new pandas data frame, just as you've seen before. So sorry, I should have mentioned, obviously we have to import pandas as PD up here. And I've also imported CSV, because we're going to need that in a moment. Sorry, I should have mentioned that. So here I'm going to create a new pandas data frame, and I'm going to have 4 columns in my data frame. I'm going to have a patient ID, the time they started queuing for the nurse, the time they finished queuing with the nurse, and the total queue time for the nurse. Okay. You probably don't in reality need start queue and end queue. I'm just showing you here. And in fact, in the exercise that you're going to do in a moment, you won't need those things. But I'm just showing you here an idea of how you could store that kind of information. You might want that information depending on what you're trying to do. So we'll have 4 columns, which represent each patient, when they started queuing for the nurse, when they finished queuing for the nurse, and the total time, i.e. one minus the other. So I set up the pandas data frame exactly the same way as I did before, except we're using self dot because it's going to live as an attribute of the model class. So the data frame is going to call results underscore df, and that's going to be stored in the copy of this model class. So each time we create a new instance of the model class for each run, we'll give it a run number, and it'll also hold its own pandas data frame that will represent the results from that run. Then the third thing we're going to do, we're going to add some methods to the GP surgery model class that will calculate the results we want to store. So we're now adding another method here. Sorry. Here we go. Number 3. So we're going to add another method to our model class that will basically calculate whatever we want. Now here, for simplicity, we're just going to have a method that will calculate the average queuing time across patients for the nurse. Okay. So remember, we've got a pandas data frame that will be storing each patient, how long they spent waiting for the nurse. And then all this method's going to do is it'll look at that pandas data frame and take the average. And that's really easy in pandas. So we're going to create the, I've just called it calculate mean queue time nurse. I'm going to store that as an attribute of this model class, so I can refer to it whenever I like. And when we call this function, what it's going to do, it's going to grab the data frame, which is stored in this class. So we need to use self dot. It'll take the queue time nurse column, which is where we store how long each patient queued for a nurse. And we'll just call the mean method on that, and it'll just take a mean of that column. It's really easy with a pandas data frame. So when we call that, we can call that at the end of the run, basically, and say, okay, now all the patients have come through. Take the average queuing time across all of them. So then the fourth thing, we're going to add another method to this model class that writes the results from the run to file. So this is the next one that we've added. So we've added another method. So we've now got 6 methods in our model class as opposed to the 4 that we have to have. And this one I've just called write run results. And basically what this will do is it'll open a file called trial results.csv in append mode. So it adds on to the end. Remember, this is going to be run in each run of the simulation. At the end of each run, it'll write these results. And just as we saw before with this kind of thing, we'll create a new writer, a CSV writer. We'll get it to write the run number alongside the mean queue time for the nurse to a CSV file. So we just basically have run number 1, the average queuing time for a nurse was 20 minutes. Run number 2, it was 15 minutes, etc. Okay, that's all that file's going to store. Fifth thing, we need to remember, so these extra methods, one that's going to calculate at the end of the run, it's going to calculate the average queuing time for the nurse, and the other that's going to write those results out to the to a file. We need to call those from the run method after the simulation run. So if we go into our run method here, so this is exactly as it was before, but here's the extra bits we've added. So here's where we tell it to start up the entity generator. Here's where we tell it to run for the specified amount of time. And then here, we're going to call this new function that we, this new method that we wrote called calculate mean queue time nurse. So once we get to this point, the run is finished. It's run for 2 hours in this case. So now go back into our pandas data frame, calculate the mean queuing time for the nurse, and then call the method that then writes those results to a file. So it'll say run number 1, mean queuing time was whatever. So we're going to call those 2 methods at the end of the run. And we'll do that for every run. Because remember, each run will be a run through the for loop. The 6th thing we're going to do, we're going to create a new class that will hold attributes and methods for calculating and printing results over our trial, over our batch and runs. So we're going to create another new class here. And this one I've called trial results calculator. And this is basically going to have a simple constructor which just stores a data frame that stores our results over the trial, over all of the runs. Remember, that's separate to the results DF that the that is being held up above. That's the one that just stores it for that particular run. This one's going to store it across the entire trial. Then we're going to have a method that will just basically print out these results. So you could have whatever you like in here, but I've decided to have something that will print out once all of the runs have completed. It'll print out the results over the entire trial. So it's just going to have a little print message here. And then it's basically just going to, all it's going to do is going to read back in that CSV file that we were writing. Every time we had a run, we were writing a new line to it with the average. We're going to read that back in once we've finished all of the runs using the pandas read CSV method, which is a really nice method, allows us to, in a single line of code, read that CSV file into a data frame with the appropriate column headers. And we'll just take the average. So we'll take the average over, if we've got 100 runs, we'll take the average over 100 runs. What's our average patient waiting time per run? And then we'll print that out. The 7th thing we're going to do, we're adding to this file that's going to store the results of each run. But in order to do that, just to make it nicer when we read in to the pandas data frame, as we just saw, let's put some column headers in at the start, because then when we read it into pandas, it'll automatically put those column headers into our pandas data frame. So we're going to here, just before we go into our for loop that's going to do all our runs, I'm just going to open this trial results.csv in write mode. Remember, if that file doesn't exist, it'll create it. If it does exist, it'll overwrite it. And that's different to the append mode we're using up above. Remember, append mode says add it onto the end of the file. So whilst the runs are going, we wanted to add each run as a new entry into that file. But here, we haven't started the runs yet, so we're going to create the file from scratch. And what we're going to basically just do here before we do anything else is write the column headers. So that's what we're doing here. I'm just going to have 2 column headers, one that will say run, which will represent the run number, and one mean queue time nurse. So the mean queuing time for the nurse for that run. And then the last thing we're going to do is instantiate this new class that's going to calculate our that we've just written, that's going to calculate our trial results after our batch of runs is completed, and we'll call the relevant functions. So down here, this is what we had before, where we run our GP surgery model for the required number of runs. Once all that's done, so say we've got 100 runs, they've all completed now. We've written all of our run results out to file. So now, once all that's completed, our trial is completed. And so now, at this point, we'll create a new one of these trial results calculator classes that I've just written up above. And I'll call the print trial results method, which, remember, that's the one that's going to read in that CSV file, put it in a pandas data frame, and then tell us what the average is over the trial. So if I run that, we can see it's going through 100 runs there, and then it tells me it's written, it's then read out, read back in the CSV file, and we can see mean queuing time for the nurse over the trial is 14.29. If I run that again, it should be fairly similar. Yeah, 16.07. But remember, if we were just doing it in individual runs, in fact, let's have a look. So this thing would have been creating a CSV file. So let's open up that CSV file. So remember, it's called trial results.csv. So if I open that up, you can see here, that's what we've been writing out on each run. The run number and a mean queuing time for the nurse. Run number 0, the mean queuing time is 3 minutes. Run number 1, it was 3 minutes. Number 2, 22 minutes. A lot of variability. And that's why last week we said, well, this is why we do lots of runs and then take the average over the runs, because we'll have runs of very good luck and runs of bad luck. We need to find out what the inherent sort of average is over that sample. Okay, so that's one approach. And there's different ways you could do it, but that's the approach we've taken here. So that's a lot of information to take in. I'm aware of that, and that's why you're going to have a very long exercise now, in order to, in your groups, to go back through this, and then to try this out yourself. So let me just make this a bit bigger for you. So what you're going to do, well, the first thing I want you to do actually, when you start on this exercise, is to, in your groups, go back through the code that I've just shown you, SimPy 001 first, to make sure you understand how the object-oriented structure works, and then look at the changes in SimPy 002 to see how you'd capture the trial results. What I suggest you do, get one person to share their screen and sort of talk through it and make sure everybody is understanding what's happening on each line, and you've understood all this. That will make the rest of the exercise much easier. So go back through and make sure you're all understanding this first. Then what I want you to do is the following. Your task is going to be, in your groups, to write an object-oriented version of this model in SimPy, where we've got, now you'll recognize this, this was we did a non-object-oriented version last week of this in SimPy 3.py, which is where we got people arriving at an ED, they queue to be registered by the receptionist, then they queue to be triaged by a nurse, and then we've got a fork where 20% of them then go off to be assessed in an ACU by an ACU doctor, but the majority of them, 80%, stay in the ED and they wait for an ED assessment by the ED doctor. And I've put all of the parameter values over here to the right. So they're coming in every 8 minutes on average, 2 minutes on average to be registered, etc., etc. I want you to run the model for a period of 48 hours after a 24-hour warm-up period. Remember, we covered warm-up periods last week. And to run the model for 100 times as well. Now, you're also going to need to ensure that this model is storing the queuing times for each queue for each patient. You don't need to worry about what I just showed you with the time started queuing, time ended queuing. You just want patient, and this is how long they were queuing for each of the queues. So patient 1 queued this long for registration, this long for to be triaged, etc. Now, I recommend you do that in a pandas data frame, much as I just shown you in the previous example. But you may be thinking, hang on a moment, you've got a branching path here that means for every patient that comes in, one of these things they're not going to have a value for because they weren't waiting in that queue. They either weren't waiting in this queue or they weren't waiting in this queue, depending on what path they go down. So the way I'd recommend you do that here to allow you to follow the structure that I've just shown you is to you replace the missing queue number, whatever it is, if they didn't go down this route, then replace that in your pandas data frame with a queuing time of nan, which represents, it stands for not a number. Now, the reason I tell you to do this is because pandas will ignore nans when it takes averages. So you don't need to. So you can then just have nans in your column, and it'll ignore them, and it'll only take averages that don't include those. And it's really easy to create a nan and not a number value in pandas. You just cast the string nan as a float, and it'll create a not a number value. I'll say they're all then ignored by pandas. Don't worry about that initially. When you come on to that bit, that will make sense. I also want you to deal with the branching path. There's different ways you could do this, but one way in which you could do this would be to have basically the probability that they're going to go down the ACU or to the ED, and some sort of flag indicating whether they're going to go to the ACU or to the ED that's stored against that patient, and a method within the patient class that determines which route they'll go down. So in other words, you kind of when you create a patient, you'll then call that method, and it'll predetermine are they going to go down this route or that route. So when they get there, you'll already know. That may not be how you do it in the real world. Depends what you want to do. But for this, I want you to do it in that way, because that will get you used to writing a method for one of your entities. Don't forget to include the warm-up period as well, and ensure you're not collecting results during your warm-up period. And don't forget to run the simulation for the warm-up period plus the length of time. So you're going to need to run the simulation for 48 hours plus the 24-hour warm-up period at the start. So I'm going to give you an hour and a half to do this, because I want you to have a look through this stuff first as well, and to get a good chance to do this. So we're going to resume at 12 o'clock. I'd recommend the first thing you do is go off and stretch your legs for 10 minutes and just clear your mind. I'll open up the rooms now, then go into your groups. And I say the first thing, decide who's going to share the screen, and just go back through the code. Start with SimPy 01. Just make sure you're understanding everything there. Elliot, sorry, yeah, your hand's on.
Oh, hi there, Dan. It looks like when we're running this code, just a couple of people mentioned it in the chat, it talks about a frame append error. I think it's only a future warning, so I don't think it's falling over, but it's just something to, future-proof the code.
Yeah, thank you. I forgot about that. So yeah, so if you're on the newer, if you've because you've all sort of recently installed newer versions of NumPy and pandas, then basically if you remember, we ran into this problem back in the second Python session where we looked at NumPy and pandas. So the append method is being deprecated. That means that basically you can still use it, but in a future version it'll be gone and you won't be able to do that anymore. So apologies, I only found out about this a few weeks ago, so therefore some of the stuff that uses pandas will still use the append method. You can still use that now, and I did put up instructions for the alternative way in which you add things onto a data frame, and we can repost that. But for now, just use the append method, but just bear in mind you will need to change that in the future, because it won't always work. There will come a point at which they'll just remove that method. But yeah, it will still work now. You'll just get a warning to say, look, this thing is going to go, so be careful coding in the future with the append method.
And I've just seen a couple of other people having issues actually opening the file. Error 9, bad file descriptor when running.
Okay, I'm not sure what that is.
Yeah, okay, cool.
Take
that offline.
Yeah, sure. As I say, it should work. You should be able to. Which file are you trying to open? One of the Py files?
Apparently, I'm just looking at the chat windows from Chris. SimPy 002.
That's odd. There's no reason why you shouldn't be able to open that file. So right. Yeah, it might just be a turn it off and on again job, I suspect. Okay, I'll open up the rooms as they go and have that sigh means you know what's happened. My Zoom has crashed. Bear with me 2 seconds whilst I'll be back in 60 seconds or less. Let me just force the close. Hello, sorry I'm back. It seems to be a common thing after the first share. So I both equally love and hate Zoom in equal measures. And at the moment I'm hating Zoom. But it'll probably work fine for the rest of the day now. So there we are. Okay, go and stretch your legs for 10 minutes. I will open up the rooms now, and then we'll be floating around. So have a go at this exercise, and I promise you it's not going to be quite as bad as you think it may be. Okay. Hi everyone. Okay, so apologies. I know I'm not sure if any of you got to them, but you were all getting there. And I'm conscious that there is some a little bit more stuff I want to just whiz through over lunch before lunch, sorry, so that we don't overrun. Most of you were on the way to it, so I won't go through the solution now, but I will obviously put up the solution. You're all on the right lines. I think you just needed a bit more time. One thing that did come up quite commonly though was some still a bit confusion, which is normal around self and the object-oriented side of things. Now obviously Elliot will go over some of the object-oriented stuff in the recap sessions, because he's covering the module 1 content in those sessions. He's also got a couple of links to some videos that will try and explain this. It can be a bit weird, but think about it in these terms, that essentially, so you've got the example of a patient class and a model class. When you write the patient class, you use the word self to refer to when I ask you for a new patient. Self dot means that's the attribute, that's the method that will belong to them. So I'm going to create a new patient called Bob, and this will be Bob. Yeah, this is where Bob will store his ID. This is where Bob will write down his queuing time, etc. Nice way to think about attributes of things like patients is to think about them walking along your system with a notepad and a pen and thinking, right, I've got my patient ID written down. If anybody asks for that, that's the ID I'll give them, and I'm going to make a note of my queuing times as I go through the system. Those are the attributes. They belong to that patient. They carry them with them across the course of the system. Now it came up in a couple of groups around, so why then in the model aren't we using self? Why are we then talking patient dot? And it's because it's kind of first person versus third person. So when you're in the patient class, you're saying these things belong to the example of patient the instance of a patient I'm going to create, which we call self. Whereas when you're referring to it externally, in the model class, for example, you're passing in a patient object that you've created, and you're saying, I need that patient's ID. It's not my ID, I need that patient's ID. So it will come. Object-oriented programming is the biggest challenge is just getting your head around the concepts. Once you've kind of got into that way of thinking, it does become easier, I promise you. So I would strongly urge you for particularly for this exercise, if you didn't manage to finish it, I would come together and try and finish that exercise before you have a look at the solution. I also say that because, and a point I haven't really made so far, but is important to make really on this program. We've moved now beyond the module 1, the introductory stuff, getting you up to speed with Python. Everything else now are kind of methods that we are showing you. You're not expected to be an expert in everything. You're not expected to like everything. You don't need to be. Within the Pencore team, we're not experts in everything. I know very little about geographic modeling, for example. That's why Elliot's going to be doing that training. I wouldn't touch R with a barge pole if you paid me. That's personal preference. We all have our own sort of specialisms and interests and things we like. And so the main purpose of this course is to give you exposure to a broad range of things, but also we go both wide and deep. But that doesn't mean that you, by the end of the course, you have to be an expert in discrete event simulation, machine learning, geographic. That's not the case. And in fact, for your projects, remember, you're probably only going to need one of these methods. You might use a couple. Natural language processing tends to be one that gets bolted into other things. But primarily, it's going to be based around one method. So my advice to you would be, if there's certain methods you like, that's fine. If there's certain methods you don't like, that's also fine. And when you're thinking about your projects, don't just think about the problems that you've got, although that's important, and what could generate the most impact, but also think about, well, what do I enjoy doing? There's no point you putting forward a discrete event simulation project if you absolutely hate SimPy, you don't understand it, you don't like doing it. Well, then do something you do enjoy, because you're going to be doing this for 9 months on your project, so you want to do something that you enjoy too. But the nice thing about the SimPy sessions is that, and obviously it's the last session on SimPy today, if you are going to do a discrete event simulation project, all of this stuff is pretty self-contained. So if you can get your head around these last few sessions, and you'll have plenty of chance to go back over it and really become familiar with it, then that's it. You can pretty much build anything. That will allow you to build. You might have some, odd things that are unique to your model, where you have to use some features that we haven't demonstrated, and I could point you in the direction of those things. But the fundamentals are all there. So you only need to get your head around those 3 sessions, and you can pretty much build any discrete event simulation model, or at least the basics of it. So that's a nice thought, that if you did decide to do a discrete event project, it's these 3 sessions that you just need to go back over and just make sure you're okay with that. There isn't, I'd like to say something like the machine learning, where you may then have lots of other, because there'll be lots of stuff that we don't cover, that you might then want to explore, and that will work well for people that want to go off and think, okay, well, we've covered that, but I want to look at random forests, which we haven't covered, and stuff like that. So just bear that in mind. So don't worry if not everything sort of fits into place initially, and particularly if you want to do a discrete event simulation project, if you're kind of that's what you've got in mind, and you're thinking you quite enjoy SimPy, just not quite there with it yet, that's fine. Remember, you've only got these sessions to look back over. I should also say, just linked to that, I think there might be some confusion around the recap sessions. So the recap sessions are only for module 1. They're only running for another 2 weeks now, so they are only for the module 1 content. There won't be any recap sessions for the rest of it, but you should be going back over things in your own time, and particularly, again, prioritize those areas that you think you are going to be most relevant for you and that you're most interested in. So if you're already thinking, do you know what, I think I'm probably going to be doing a discrete event project, prioritize looking back over this stuff in the last couple of weeks, because that's what you'll need. Okay, so I won't go through the solution now. I managed to get through virtually all of the groups, I think, and you're all on the way to it, and most of you got pretty much all the way there. You were just sort of fiddling around with some of the extra bits. So I think you're all okay, but I will obviously post up the solution and you can check it. But I would urge you to try and finish off what you were doing, because it looked really good. What I saw, you're all on the right lines. But I did want to, I don't want to overrun, so I'm just going to very quickly run through a couple of extra things that are probably going to be, one of them in particular might be quite important for some of your models. I'm not going to go through them in detail. I'm going to show you broadly how you would do this. I've given you the code examples that you can look at in your own time as well. And what I'd recommend is then, if you need to do these things, to look back at them. And you might want to look back at this part of the recording when it goes up on YouTube, and then sort of just pause it and then have a look at the code as I'm going through things. That's the nice thing. You can pause me when you're viewing the recording. Okay, so let me share my screen, and we'll go over these last couple of things before lunch. Where are we? The good news is this afternoon is nice and light. So we're talking about quite an exciting area this afternoon, but you'll be pleased to hear there's no coding. I've got you a nice fun task that before we start sort of coding on this. So there's no the heavy stuff is this morning, and then we've got a nice, hopefully very interesting example this afternoon. Okay, so let's first of all just talk about priority-based queuing. So remember last week when we introduced discrete event simulation, we talked about queuing policies, and we said that the default queuing policy is FIFO, first in, first out. That's the default queuing policy. If you don't specify anything else, that's what SimPy will use. It'll say, well, that person arrived first, so that person will be first in the queue for a resource. Now that's fine for a lot of queues, and there's a reason that's a default. But particularly in things like healthcare systems, you probably in some queues want some element of prioritization. You don't in an emergency department, for example, strictly see everyone in the order in which they come in. They are triaged and prioritized, and they have some sort of prioritization. You don't say, well, this person's having a cardiac arrest, but I'm sorry, this person with the broken thumb came in first, they'll have to wait. We prioritize people. Okay, so there will be examples where you want to do this. Now, SimPy has a really neat feature that allows you to do this pretty easily, to actually turn a queue into a queue where you can have prioritization. And to do this, we use something in SimPy called a priority resource. So you've seen the resource class. That's what we've been using so far, the SimPy resource class. We say we want a nurse, that's a SimPy.resource. But we can actually use something called a priority resource, which is like a normal resource, but it allows them to see entities in a queue in some sort of priority order. So I'm just going to rattle through very quickly the bits you'd need, and then I'll show you the code running so you can see it in effect. But then, as I say, after the session, I'd advise you to go back and have a look through the code itself. Most of it will be the same as what you've seen this morning. I'm using the same example, but I'm just adding in these features. So up until now, we've used the standard resource class when we set up a new resource. We need to use the priority resource class if we want a queue for a resource in which we want that queue to be in some way priority based. Okay, we instantiate a priority resource in the same way as a normal SimPy resource by telling it the environment in which it's going to live and its capacity. Okay, so exactly the same structure you've seen before. It's just, instead of saying SimPy.resource, we say SimPy.priority resource. Okay, but we still pass in the environment and the number of that, the capacity, the number of resources we need of that type. So we just use priority resource instead, and then SimPy knows, okay, this is when people are queuing for this resource, we may have some element of prioritization in that queue. Now, the way it works is that the priority resource will look at the entities that are queuing for that resource, and it will look at an integer variable that we tell it which variable to look at, and it will look at there will be an attribute of that entity. So if it's our patient, some attribute, we say that's the priority attribute, and it will use that number to determine the priority of that entity, patient, whatever it may be, with lower values representing a higher priority. Okay, so if you had two patients come in, one's got a priority of 1, one's got a priority of 2, the patient with a priority of 1 will be seen first, even if they came in after the patient with a priority of 2. Lower number, higher priority. Okay, so the way we do that, so here I've changed the code so that in the patient class they also have an attribute called priority. It's not very imaginative, I could call it anything like, but I've called it priority here, and I've set that to a default of 1 for all patients, and then I can amend it however I like. I've added in a little method here as well that will determine the priority. Just for simplicity, this method just randomly picks a number between 1 and 5 for that patient and then gives them that priority. But you probably want something a bit more sophisticated. In your own model, you might say, well, 20% of patients coming in at the highest priority, so 20% of them will get that priority, etc. And then I'll call that method when we create a new patient. So I can say we've created a new patient and determine what their priority is. I could have for this, because I'm just random, I could have just put it in here, but obviously you wouldn't in reality just have all patients being equally likely to be very high or very low priority. So we've got a priority resource set up instead of a normal type of resource, and I've added an attribute to the patient class that allows them to carry with them a priority, an integer value which represents the priority, with a lower value indicating a higher priority. We also need to tell the priority resource which variable, which attribute I've used that it should look at to determine the priority. Because just because I've called it priority, it doesn't mean that's the one I want to look at. So we do that at the point at which we request the resource. Okay, so far you've seen this structure with self dot name of your resource dot request as REQ. What we do here, we can put stuff in the brackets when we do the request, and we can set priority equals, and then here we specify the variable it needs to look at in order to determine the priority. That's the integer variable. which remember in my case was the I've put in a priority attribute of the patient class. So patient dot priority means have a look at the priority attribute of the patients that are in the queue. And it'll use that, and SimPy will do everything else for you. Now you've told it this is a priority resource, so people queuing for it will be prioritized, and you've told it how they will be prioritized, and it's based on this attribute. So then SimPy will automatically look at those patient dot priorities coming in, and rather than doing it as a first in, first out for all patients, it will look at priority first. So let's have a look. I'll just run. I won't go through all the code because those are the code changes. You can look at it in your own time, but I'll just show you that running. So if I run that code, here we can see if we just scroll up, for example, see if I can find a good example. Probably can't. Hang on. Sorry. Let's go back to the start. Okay, so here the first patient comes in the first run, and they come in with a priority of 1. They're waiting, so that's the highest priority. They're waiting to be seen. They get seen. Then we get a patient with priority 2 is waiting to be seen by the ACU doctor, but that patient comes in and they're still priority. Another patient with priority 1 comes in. Another patient with priority 1 comes in, etc. So now we've got a situation where we've got the first patient with high priority came in and they were seen. But then we've got 3 new patients, 18, 23, and 25, who've joined the queue. 2 of them have got priority 1 and 1 of them has got priority 2. Priority 2 came in first. But the next patient that's seen is patient 23, which is the first patient that came in with the highest priority. So first in, first out is used to break ties when you've got the same priority level. So we've got 2 patients with priority 1, and so the one that came in first is seen, but they are seen before patient 18, which had a priority of 2, a lower priority. Okay, so you can see that that in action, and that can be really useful for some of our queues. It may not be that all of our queues in a system need that, but some of the queues may be priority based, and it's really easy to do that. You just use the priority resource class and you tell SimPy which attribute to look at that will determine a priority, and it just needs to be an integer where the higher the number, the lower the priority, and vice versa. So that's how you prioritize. And just very quickly, I'll go through the other thing I just wanted to mention, which is resource unavailability. So far in our models, we've basically assumed that outside of the things we've modeled, the things we've captured in our model, that our resources are always available. Okay, so if they're not working on the things we've modeled, they're ready and waiting, and if we need a doctor, they're there. But of course, that isn't always the case. It may not be that your resources are always on shift, and depending on the span of time that you are looking at in your model, it might be they go off shift at certain times, or it might be you've just modeled one part of the ED, but that doesn't mean that the doctors and nurses are just working in the bits you've modeled. They may be doing other stuff that you haven't modeled. And if you don't capture that in some way, then you're going to be underestimating your resources, because you're going to be thinking, okay, well, everything's fine because the doctors and nurses are always available. That's because they're actually not. They're doing other stuff that you haven't captured. Now we can capture this unavailability of stuff that we're not modeling in SimPy quite easily by obstructing a resource by a certain amount of time. So let's think about an example in our ED model. Let's imagine our ED doctor isn't always available for part of the system. Now, it may not be the same ED doctor in each case. It might be, for example, let's say you've always got 2 ED doctors, and those doctors will change every so many hours, but there'll always be 2. In which case, you don't have to worry about this, because as far as SimPy is concerned, there are 2 ED doctors. Doesn't matter that they're different. There are 2 resources. But if you've got a situation where you've got 2 ED doctors, but then for 5 hours you've only got 1 ED doctor, then that is a difference that you need to capture, because you've got a decrease in the total resource. Or it might be that the ED doctor is doing other stuff that you haven't modeled whilst they're on shift. They're going off and doing other bits in the department, or they're called away to other bits of the hospital. So here we're just going to set up a really simple pattern to represent that they're not always on shift. And we're going to set, we could set up a bit of randomness around that, but we're just going to, and you probably want that if you are modeling them being called away to do other stuff. You'd want a bit of variability because it may not always be the same amount of time. But here we're just going to pretend that we're modeling shift patterns, and we'll assume they're fixed. So we're just going to use fixed period of unavailability. So we're going to set things up so that every 8 hours in our model, an ED doctor is unavailable for 4 hours. In other words, we are an ED doctor down for 4 hours. Okay, every 8 hours. So what we'll do is we can put in some new attribute values in our G class, so that we can easily change these things. So here I've got the unavailability time, so how long they would be unavailable when something's unavailable, and the unavailable frequency, which is how often this unavailability will kick in. So 4 hours here and 8 hours here. Every 8 hours will make it so that we're an ED doctor is called away for 4 hours, representing the end of their shift. The way we're going to model this is by setting up another entity generator. This doesn't actually represent any patients coming into our system or any form of entity. Instead, it'll represent an abstract entity that doesn't really exist, but will essentially have a higher priority than everything else in your system and will pull that resource away. Okay, so essentially it comes in and this entity demands a doctor, but this it's basically just an abstract entity. It's just saying it's representing them. Perhaps it's, you know, their partner calling them away to be at home. It's something that will take priority over everything else. So we've set up a little definition of a new generator here, and what we'll do, the first thing we'll do in that generator is we'll freeze for the amount of time that we specified as our frequency. We said every 8 hours we'll lose one for 4 hours. So here the first thing we'll do, freeze for 8 hours. Don't do anything for 8 hours. It's all fine for 8 hours. This generator can just wait. It's not going to do anything. But then after that 8 hours, we're then going to request, this generator is going to essentially request an ED doctor with a priority of -1, which means, remember, the lower the priority value, the higher their priority. Therefore, a value of -1 is lower than all of the other priorities. We're using priorities between 1 and 5 in the rest of our model. So -1 means this gets priority over everything else. Then what we'll do is we'll just, in the same way as we had before, we'll hold that resource for the amount of time that we specified, which in this case was a fixed amount of time, representing 4 hours being off shift. Okay. Now, this doesn't mean, just because we've given it a higher priority than everything else, it doesn't mean that when this patient, this entity comes in and says, I want to grab a doctor now for 4 hours and I take priority, it doesn't mean the doctor will immediately stop what they're doing and then take priority, because that wouldn't happen in the real world. You wouldn't have the doctor say, I'm sorry, I'm in the middle of this, but I've got to go home now for my dinner, and then just walk out. Okay, so they would typically finish what they're doing first. So this will work the same way in SimPy. They'll finish with the current, whatever their current activity is. At that point, they will then leave, and they'll be essentially held for 4 hours in this example. The only other thing we then need to remember to do is to then set up that process generator, that generator that's going to cause an obstruction, set that running in our run method. So if we have a look again, I won't go through the code now, but and those are the changes that I've just described. That's the only changes I've made, but let's just run that so you can see how that would work. So here in our run, it says an ED doctor will be removed around time 480. So at the start of the model, they're going to say in 8 hours, I'm going to remove an ED doctor. Around that time, though, because it won't be on the dot, because if the ED doctor's busy, we'll have to wait for them to be free. Then an ED doctor becomes unavailable, that happens, and then they'll be back at time 732.8. So because we've got the decimal point there, that's implying, yeah, there was a bit of time. It wasn't on at 480 on the dot, that we had to wait a little bit. And then when they come back, they'll then be an ED doctor removed again at time 1, 2, 1, 2.8, etc. So essentially, the ED doctor is still in the system, but they're being held, and they can't be used by anything else. So it models them being unavailable. And you could use that to model shift patterns, or you could use it to model them being unavailable because they're doing other stuff. I'd say have a look back through this stuff in your own time. I'll share the code so you can have a look back at it. But if you need to do this kind of stuff in SimPy, hopefully you can see it's actually fairly straightforward to do that. Okay, I'm going to stop talking there and let's break for lunch now. When we come back, so we'll have an hour's break. We'll come back at 1:35 and we'll resume. You can stay on the call. If you do stay on the call, just make sure you're muted and your camera's off. We'll start again at 1:35, and this afternoon we're going to introduce ourselves to the world of AI and machine learning. So a nice fun task I've got for you this afternoon as we start to dip our toes into the world of AI. Okay, see you in an hour. Okay, good afternoon, everyone. Hope you managed to have a good lunch break, and welcome back to this afternoon session. So, this morning we finished our discrete event simulation module, and then this afternoon we're going to be starting on the next module in the program, which is machine learning and AI. Now, I have to say, this is probably, if I'm honest, the most difficult module of the program. But I would also say convey stuff that is probably some of the most powerful stuff that you will see on the program as well. I flagged that up now because it's important that you're kind of aware, because some of the methods are a bit easier to follow than others. The machine learning, we are aware it is a little bit more complicated, and so the training has been designed to ease you in gently. We also by no means try and teach you everything. So unlike SimPy, the sessions you've just been doing over the last week and a half, those sessions are very, as I said this morning, quite self-contained. There's other stuff that we don't cover that you can do in SimPy, but most, if you just took the training that you've done over the last week and a half, you'd be able to get quite a long way in SimPy. The machine learning, we can't possibly hope to do that. So this is a bit of a gentle introduction today to some of the key concepts of machine learning, and to get you thinking about some of this stuff. And over the coming weeks, we'll gradually introduce you to more and more. And the key things that we will do is talk about some of the ethics of AI next week, which is hugely important. We'll then show you how to do some simple logistic regression-based models to get some really powerful learning. We'll then show you how we'll talk about neural networks and how what neural networks are, and how we can use neural networks to create very powerful learning algorithms. And we'll also touch on synthetic data, creating using AI-based techniques to create data that is completely made up, but is so good that it can be used as a substitute for real data. So all of that's to come in the machine learning module. But today we're just going to have a sort of gentle introduction. So there's no code this afternoon, which will be, I'm sure, delighted to hear, and get a bit of a break. And hopefully we've got quite a fun introduction to this stuff, because it's important that before we get on into all that actually you do understand the fundamental concepts of machine learning. So let's talk about AI first. What is AI? So AI, it stands for artificial intelligence. It's been around for a long time. It refers to the way in which we can simulate either intelligence itself or some aspects of intelligence used by machines. Aspects of intelligence that we might want to simulate might include things like learning. Learning is an aspect of intelligence. And what do we mean by learning? We mean being able to make decisions, such as classification decisions. So a lot of the examples that we'll show you in this module will revolve around classification type problems, where we are predicting whether something belongs to one class or another. And that's a very powerful machine learning tool. There are also things like reasoning, which is where you are trying to apply logical rules in order to come to some kind of conclusion. We have intelligence by machines where they try to have coherent conversations with us as human beings. Indeed, many of the early AI competitions were designed around exactly that. Being able to create intelligence was deemed as, if we created a machine that's intelligent, we can have a conversation with it, and we wouldn't be able to tell whether it was a machine we were talking to or another person. And there's also aspects of intelligence such as perception, so being able to recognize things like images or speech recognition is a big thing these days, or other sounds as well. Now in the course we're going to focus predominantly on learning, on being able to teach machines to be able to make decisions such as classification decisions, because that's the kind of thing that you're likely going to want to use for a lot of your projects, and which will have the most impact for the sort of problems you would want to look at. And specifically, we're going to look at trying to simulate human decision making, which we will do in this module, and trying to learn patterns in natural language so that we can automate the extraction of information from free text, which we'll cover in the natural language processing module, which comes directly after this module. So that's what we're focusing on, but it's just to sort of flag up that there are other aspects of AI and machine learning that are out there. This is by no means exhaustive, and these other aspects are equally fascinating, but perhaps have less direct utility for some of the things that you will likely be doing. So what do we mean by machine learning? Machine learning is basically a field of artificial intelligence. So we've just seen there's many different ways in which we can create artificial intelligence, but machine learning is the one we're focusing on, and it's a subfield of AI, which is all about trying to develop algorithms that enable a machine to learn by experience and by being presented with data, and additionally, in some cases, being presented with the answers to help it learn. And we'll come on to that in a moment. So typically, when you're building a machine learning algorithm, you're trying to make some sort of prediction or classification about something, given some data about it. And this might be that you're trying to provide some decision support to a human who has to make those decisions, because you're trying to get the machine to learn inherent patterns within the data that we might be conscious of or we might not be conscious of. So there might be things that we don't know how we're coming to these decisions, but a machine might be able to unpick those sort of hidden patterns that we're unconsciously seeing in order to replicate that kind of decision making. And it's important that we stress that typically, for the kind of things you'll be doing, you're not really building AIs that will take over from a human. So in Mike's presentation tomorrow, and Mike and Anna present, they'll be talking about using stroke data to try and teach machines how to determine whether a patient should receive clot busting treatment or not, because it's not everybody that can receive it, and there are risks. The object of that is not to replace the stroke consultant. It is to provide some information to the stroke consultant to help them make a decision. And that's very important, that we're not looking to build machines that are trying to take over. Well, unless you're building Skynet, of course, in which case ignore everything I've said and go off and do your evil bidding. Okay, so let's talk about some of the pros and cons of machine learning. Some of the pros. Machine learning allows us to automate things that are done by humans that would consume either time and or money resource. Okay, so things that it can help us speed up our processes, because it can help do things that would require some of our resource to do. It can also help us to try and better understand some of our own decision making, or to try and unpick some of those patterns, although there's a big disclaimer around that. And when we come on to talk about neural networks in a couple of weeks, you will see some of the black box problems of machine learning, and specifically neural networks, but that there's a growing field of something called explainable AI, which tries to unpick some of this magical decision making that the machines are doing. And we're trying to allow our data to be used to generate some sort of insight about something. Remember, back in the first session of the course, we talked about the difference between OR and data science. We said OR starts with a system, and you build a model that tries to replicate that system and tweak it to see what might happen. That's what you've seen so far in discrete event simulation. Discrete event simulation is a classic operational research method. Machine learning is possibly a classic data science approach. Here, with data science, we're starting with the data, and we're trying to learn something from the data that will help generate insights or help us make decisions. So we're not starting the system and then using data to plug into a model. We're starting with the data itself. And machine learning is, and AI generally, is hugely useful and hugely powerful, and it can do a lot of stuff. But it's also worth stressing that it's not a panacea for everything, which it often gets sold as, I think. It's very important to recognize that machines can and will get things wrong. Okay, and there may be ethical considerations, particularly when they get things wrong. So next week, before we show you in the morning, we've got a whole session on ethics and AI. And there's a reason for that, because the things we're going to show you, if you're not careful, you can end up destroying people's lives, whether consciously or not. And so it's very important that before we go showing you how to do all this, that you have an appreciation of what can go wrong, so that you can take measures to make sure that doesn't happen, or to mitigate against the impact of it. Because this is powerful stuff we're going to show you, and these things can and have had severe negative consequences on people's lives. So you need to be aware of that. As much as it's a positive, powerful force for good as well, it can also be misused, whether consciously or unconsciously, and therefore can be very dangerous as well. And it's also worth flagging up that you may end up, in the process of doing this stuff, of having more questions than answers. You may end up, those of you who came to the presentation event for HSMA 4 recently, back in September, you would have seen one of the presentations was talking about an AI project that just failed. It did not work. They could not get it to predict what they wanted, and so they were left with a lot more questions. But that in itself was useful, and it was a useful process to go through. But you need to go into an AI project with the kind of mindset that this might not work. We may not be able to build something that predicts this. We may learn something. Hopefully we will learn something in the process of doing it, but this may go completely wrong. And now that could apply to all of the projects that you could you could try and build a discrete event simulation and find you haven't got the data you thought you had, but at least that's a little bit more constrained. Whereas you can sort of that with a discrete event simulation you can map out what you need, and you can determine if you've got that data. With machine learning, it's a bit more of an art form, and you won't know until you try a lot of this stuff. Okay, so when we're talking about that we want to teach a machine to make a prediction or some sort of classification, what we mean in very specific terms is that we want it to predict an output given a set of inputs. Okay, now an output in machine learning is known as a label, and the inputs in machine learning are known as features. Okay, so imagine you've got a table, and your features are all of the columns in your data. Things like a person's BMI, their age, whether they've been readmitted. If you're trying to predict somebody's admission to hospital, for example, those would be the sort of features that you might have. You're trying to learn to say, okay, given this set of features with these values, I think the patient's going to be admitted or not admitted. And that output, if they're going to be admitted or not admitted, is known as the label. So your features are the inputs, and from the features, you're trying to predict the label, the output. So some examples, you might be trying to predict whether a patient's got a certain condition or can receive a certain treatment, as in Mike's work that we'll be talking about tomorrow. And you might have information about aspects of their health, demographics, time since onset of condition, etc. You might be looking to try and predict the likelihood of someone reoffending based on features such as the nature of their original crime, or whether they served a custodial sentence, etc. So the label is, will they reoffend or not? And the features are all the things from which you are trying to make that prediction. You might be trying to classify whether the image presented is an image of a flower, or whether some text that you're seeing is positive or negative in tone. And you'll have a chance to do that in the sentiment analysis session of the natural language processing module. So let's have a look at a simple example here. We're going to try and classify whether someone is a Pencordian, a member of our Pencord research team. And let's imagine these here are our features. We've got whether they like programming or not, whether they've got questionable fashion sense, their age, and their height. And those are our features, those 4 columns. And then here, this is our output, our label. So 1 means yes and 0 means no. Using the standard Boolean terminology. And so this person likes programming and they've got questionable fashion sense, they're age 40, 170 centimeters in height, and they are a Pencordian. And so what a machine is trying to do is trying to say, okay, if I were to cover up the label column, can I predict the label based on these features? Can I predict? And are there hidden patterns in there that I'm able to see? Now, in machine learning, your features, in this case, these 4 columns, are weighted. They become weighted by whichever algorithm you're using. So the weight of a feature essentially represents its contribution, relative contribution towards making a prediction. So we can work out which features are more important, which features are less important. The way in which machine learning algorithms work is essentially fiddles around with these weights such that it works out which things are contributing more to this prediction. So looking at the this above table here, what do you think some of the features are that are more important for predicting if someone's a Pencordian?
Likes programming.
Yeah, that seems like a good one. Any others? So likes programming would seem to be a pretty good predictor. It seems to be, just glancing at it, because let's look at we've got a data set here. 3 people who are Pencordians, the 3 ones, and 2 people who aren't. Of the 3 people who are Pencordians, all of them like programming, and the 2 people that aren't Pencordians don't like programming. So that would seem to be, looks like that's going to be a pretty strong predictor based on the data that we can see at the moment. Okay. It might also be that has questionable fashion sense might be quite a good predictor as well, because here we've got 3 people that have questionable fashion sense and 2 of them are Pencordians. So it might be that that's actually quite a good predictor, and maybe those 2 things together are particularly important. It doesn't seem to be much of a relationship in terms of age here. Our 3 Pencordians seem to be quite varied. There's about 40 years range there. And there doesn't seem to be anything going on with height that we can see anyway. So if we had to make an initial stab at that, we'd say a Pencordian is someone that likes programming and has no fashion sense, which is actually quite accurate. So there are 3 main types of machine learning algorithm. Now, most of the stuff that we cover in the course is going to be this first one, supervised learning, but I'm going to mention the other 2. We're not really going to touch on unsupervised learning very much, but we are going to have a session on reinforcement learning in the new year. But most of the stuff we're looking at is going to be supervised learning. So supervised learning, these are algorithms in which the machine that is trying to learn is shown examples of the features, the inputs from which it's trying to learn, and the outputs, the labels. And that's what's known as a labeled data set. Okay, so we provide it with data like this. We give it here. It's got essentially the data from which it's trying to learn and the answer. Okay, that's known as supervised learning. We show it examples to say these people are Pencordians, these people are not Pencordians. Here are the features of people with, who are Pencordians. Here are the features of people who are not Pencordians. And gradually it improves itself by getting better at getting from a given set of inputs to the correct output. So it tries to get better at saying, given these inputs, can I get to a 1 for this? can I come up with a rule where I get to a 1 for this set of inputs, but this set of inputs will get me to a 0? That's what it's trying to do. Now, supervised learning problems tend to either be classification problems, which is mainly what we'll be looking at, where you're trying to predict a discrete class, or regression type problems, where you're trying to predict a continuous value. So it might be things like house prices that you're trying to predict. So that's supervised learning, and that's mainly what we're going to be focusing on. But it's worth also flagging up there is something called unsupervised learning. Now, unsupervised learning, as you might have guessed, refers to algorithms where they don't have access to the label data. So in other words, we give them the features, they know about the input data, but they don't have the answers. And instead, what they try to do is try to find inherent structures in the data and usually try to cluster it together. So cluster together similar things. And unsupervised learning is useful where we don't have the right answer, usually because we can't know. We don't know. And so we provide it with, we don't know what the answer is. So we're essentially setting the machine off to just look to see what kind of patterns it can find. Then we've got reinforcement learning. So my PhD was in reinforcement learning, mixed with agent-based simulation. And reinforcement learning is where you have algorithms that learn by taking actions, and they either get rewarded or punished, and the machine will gradually learn to do things that lead to greater reward and avoid things that lead to punishment, usually the absence of reward, or sometimes negative reward. And this is how animals learn in the real world. They learn via reinforcement learning. Where they get rewarded, they learn to do things that lead to reward. And that isn't just, you know, trying to train your dog. That's how animals forage in the real world. They work out. A bee flying around will gradually learn where it can find nectar in flowers, because it's an energy efficient forager, and it needs to find as much food as possible as quickly as possible. So it learns by reinforcement learning. Now, we're going to focus, as I say, mainly on supervised learning. We are going to touch on reinforcement learning at the end of the course as well, because it's a fascinating area. There is also something called semi-supervised learning. Again, we won't really touch on that, but this is where we've got label data for some of the examples, but not all. Okay, so we said that supervised learning is basically about classification type problems and regression type problems. So let's start with classification problems, which is mainly what we're going to be focusing on in this course. So classification problems are ones in which we're trying to predict to which class an example belongs. Now, those classifications might be binary, where we've got two classes, and usually that's true or false, yes or no. So a lot of the classification problems you'll be looking at are things like, is the patient going to be admitted in the next 3 months? That's a binary classification problem. Does the patient have this condition or not? It's two classes, yes or no. So binary classification is one of those common things that you will end up using. There is also something known as multi-label classification there as well. Sorry, there's also multi-class, which is where it goes beyond binary. So there might be 3 or more classes. But there's also something called multi-label, which is where we don't just have a single output for each set of inputs. We might have more than one label or class for each example. So let's think about some examples of this. So a binary classification problem, the kind of problem you're going to be looking at and we'll be focusing on in this program. Does this patient have condition X or not? That's an example of a binary classification problem. And that's something that that you might try and teach a machine to work out. Given these features, can you predict whether the patient has that condition or not? Which condition does this patient have would be an example of a multi-class classification, because there's more than 2 classes, and so you're trying to work out, you know, of 8 conditions, which one does this patient have? Or you might have a question like, what are the multiple conditions that this patient has? And that would be a multi-label classification, because each patient doesn't just have a single classification. It has potentially multiple classifications to list all of their conditions. So those are classification problems. Then we've got regression problems. So regression problems are ones where we're trying to predict a continuous value as the output, for an example. So the outputs are often used to represent the probability of something being true or not, but they don't have to be. So you might have a problem where you use it to predict, what's the probability this patient will come and see the treatment, or they're going to be admitted to hospital. But often regression problems are also used for things like, what a house price is going to look like in 3 months' time, based on these set of features. And so there's we've got a forecasting module in the course. We won't go into some of the neural network based stuff, but we do have some videos from my colleague Tom that if people are interested in looking into that, that's exactly the kind of problem that looks at. Okay, let's just before we move on, let's go and have a sort of 10-minute chat, 10-15-minute chat. So what I want you to do in your groups, I want you to spend the next what time is it now? Nearly 5 past. So we'll bring you back just before 20 past. I want you to go in groups and just have a chat about some potential ideas that you can think of for that fall into some of these groups. Ideas for maybe supervised learning, maybe you have some ideas for unsupervised learning problems, reinforcement learning problems, etc. And I probably won't I may ask a group or two to share depending on time when we come back. So I'll open up the breakout rooms now. Go and have a chat based on what you've heard so far on ideas that are sort of coming into your head for how this stuff might be used. Okay, let me open up the rooms for you. Hi everyone. Okay, so welcome back. So hopefully that gave you a bit of a chance to have a chat about some potential uses of machine learning. Just very quickly, does anybody want to just feel free to shout them out? Any ideas you came up with in your groups about how this stuff could be used?
Supervised, you could say whether somebody is likely to buy a product or not in a supermarket, so based on whether people have bought it before.
Yep, that's in fact I suspect that is being used. I'd be amazed if that wasn't happening. Yeah, they're very good. Yeah, that's exactly, you could train it based on certain features of the person and the product, and then make predictions about whether they are likely to make a purchase or not. So yeah, good one.
I was going to say similar, but with like say Netflix, like recommendations in terms of like suggesting.
Yes. So funnily enough, so interestingly, you picked up on Netflix. Netflix actually uses reinforcement learning. In fact, not just in terms of your recommendations, but I don't know if you ever noticed that the images that you see for for the various TV programs and movies, have you ever noticed they change? The reason they're changing is because they're trying things on you. To see whether it causes you a particular image, whether it's likely to make you click on it to watch it. And it learns by reinforcement learning. And so it'll try out different images on you and see if you're, based on what you click through, it'll try and give you more images that are like that for other programs that it wants you to try and watch.
Yeah, I've seen on social media, on Instagram do it as well, don't they? Instagram have that algorithm where what you click on is what you see more of.
Yeah, absolutely. That's a good example of reinforcement learning. It's big. The reward there is you going through and viewing content, accessing content, and so it learns to do that thing more. Whatever it was that it did then to get you to click through, it's going to do that more.
You have the same with adverts on things like Facebook and that.
Yeah.
So yeah.
Yeah, absolutely. Yeah. Okay, so feel free to put them in the chat, any ideas as well as we go along, and pop them on the Slack channels as well. And hopefully, as we go through this module, you'll start to come up with some potential project ideas that you can actually work on for your own organizations as well. So let me share my screen. Oops, what have I done? Sorry. Try that again. Okay, let's resume. So let's talk a little bit more about some of the aspects of machine learning that you'll need to become familiar with. So these are some of the kind of core principles, much as when we talked about discrete event simulation, we talked about some of the core building blocks, things like, you know, generators and sinks, and they're probably all sort of sunk into your head now. But here are some of the key concepts that you'll see time and again in machine learning. One of the first is the concept of a train test split. So when we're doing supervised learning, we're trying to teach a machine to predict something given some data which has the answers. Okay, that's what supervised learning is. So the data that we give it that has the answers as well, are they a Pencordian or not? Did they buy this product or not? That's known as the training set. That's what we give it to learn. And the training set basically contains examples of all the combinations of feature values and the corresponding label, i.e. the answer. Once the algorithm's learned, though, we need a way to check to see how well it's learned. And that's particularly important for something that we'll come on to in a moment. So the way we do that, we need to provide it with some data that it hasn't seen yet, but which also has the answer, so it can check, okay, I've learned based on this data. Now you've shown me some new data that I haven't seen. Can I apply the same rules that I've learned? And if I apply those same rules, how good am I at predicting on this data that I haven't seen yet? And that's why you need the answers as well in the test set. And that's known as the test set. And the whole reason you're doing this is you're trying to make an algorithm that is generalizable. It's all well and good creating something that will learn the data, the nuances of the data that you give it. In fact, it's very easy to do that and get nigh on 100% accuracy. As you'll see in this course, you'll get very high accuracy with quite simple approaches, because actually these things are quite powerful. But that's no good if it's not then generalizable, if it's come up with something that is too specific to the training set, and we'll talk more about that in a moment. So essentially, we've got our labeled data set. Remember, that's the data set that we use in supervised learning, which has the features as well as the labels, the answers. And we carve off a bit of it as our training set. We give that to the algorithm and say, use this to learn. Here are the answers that you need to come to. Here are the features. Can you learn how to get from these features to that answer? So that's what it uses to learn. And then once the algorithms come up with its rules, then we test it using the test set. We say, okay, well, here's another bit of the data. We didn't show you that before. We've also got the answers for this. Now apply what you came up with during training for the training set. Apply those same rules. How well does it work on this data you've not yet seen before? Yeah, sorry, there's a hand up.
Hi there, just a quick question. So sometimes you see like subtleties with the terminology used. So I've seen references to dev data sets, for example. Would that just like depend on the context, or are there different sort of ways this is split? So for example, I've seen an example of something which uses training data, but then dev data as well, but that's probably the test set.
Yeah, they might be talking about validation sets, which I'll come on to in a second.
Okay.
That might be, but it is, yeah, the standard terminology for machine learning is training set, test set, and then something called a validation set, which I'll mention in a moment.
Okay, I think it is that. Cheers.
Oh, in fact, I'll mention it now. That was a good cue. Okay, so you're also going to hear later in the course about these things called validation sets. And doing a train validation test split. Now, basically, what a validation set is, it's like a test set, but we use it while we're still tuning things in the model. So the test set is where we've kind of, okay, we've learned, we've developed the model, it's now learned, let's see how it performs in the big wide world. And we've saved this bit of data to check, see how well, when we send it off to do the thing we need it to do, how well we think it's going to perform. But a validation set is a bit like that, but we give it to it before we finished all of the training. So we still train it on the training set. Then we use the validation set as a kind of interim glance to say, okay, the algorithm's come up with this. How good is this? And then we can use that to try and fine tune the model and say, actually, it seems to be picking up too much over here. We'll tone that bit down a bit. Let's try it again until we're happy. And then once we're happy with how we how the machine has learned, then we would do the final test on the test set. So the test set is kind of your final test. And validation sets are quite commonly used in neural networks, which we're going to come on to in a couple of weeks, where you do have that validation set. And there's you'll see when you use TensorFlow, which is the Google structure that we're going to be using in the course, that it has built-in methods that allow you to say, this is my validation set, this is my test set, and it'll automatically do those things for you. So here, this is a train validation test split. Again, this is our labeled data set. We've carved off a bit to be training data. We've still carved off a bit to be test data, but we've carved off this extra bit over here that we can use before we get to that sort of final furlong, if you like. Now, something I was sort of touching on a moment ago is a problem known as overfitting. This is a very, very common problem in machine learning. In fact, as you'll see later in the course, it's good practice to develop an algorithm that overfits initially. What do we mean by overfitting? Let's have a look at an example. So this is the table that we saw earlier, okay? And here we were trying to work out if somebody's a Pencordian or not, and this is the data, these are the features that we've got, and that's the data that we saw. And we said, quite rightly, from the data we've got, okay, it seems to be likes programming seems to be a pretty strong predictor, and maybe questionable fashion sense might be quite useful as well. Seems reasonable. Let's imagine that was our training set. Now imagine this is our test set. Here, we're trying to apply the same rules. So the rules we came up with were basically likes programming is the strongest predictor, and has questionable fashion sense may also be a strong predictor as well. But let's have a look at what's happened here. So here we've got some new data, exactly the same format, exactly the same features with labels. We've got some information about other members of the Pencord team now. So this one, likes programming, questionable fashion sense, we'd probably predict that they're a Pencordian, but they're not. This one doesn't like programming, doesn't have questionable fashion sense, they're not a Pencordian. That kind of chimes with what we saw before. Here they don't like programming, but do have questionable fashion sense. They are a Pencordian. So that kind of chimes, but we expected them to like programming. This one down here likes programming, doesn't have questionable fashion sense, is a Pencordian. This one is a Pencordian despite having neither of these things. And this one's not a Pencordian despite liking programming. Okay, so it doesn't look like, so the training set, we concluded likes programming is a very strong predictor, and this one's probably pretty good as well. But then testing that out on the test set, we can actually see that likes programming and has questionable fashion sense generate as many no's as yeses. So they don't seem to be very good predictors at all. And in fact, what we've done here is we've found something that is too specific, too unique to the training set. It just happens that the data that we've seen has led us to a conclusion, but actually that's not a it seems that's not a generalizable conclusion, because presented with some additional data, it turns out that's not a very good, these aren't very good predictors at all. Now, this is known in machine learning as overfitting. So when we talk about training in machine learning, training is known as fitting. You're fitting a model. You're trying to essentially, you're trying to fit a function, fit a line to your data that separates your data from one side. One side is one classification, the other side is the other classification. You're trying to fit a line. It may not be a straight line, as you'll see. It can be a very complex, multi-dimensional line, but it's a line. So fitting is used to determine used as a way of saying training. So overfitting means you've trained too much. The machine has trained so much that it's become fantastic at predicting on the training set. It's getting it right 100% of the time nearly. But you give it some new data, and it's rubbish because it's learned stuff that is too specific to the training data and doesn't actually have wider use. And that typically means you've got a useless model, because you're not building the machine learning algorithm to predict what you already know. You're building it presumably to predict stuff you don't know and to help you for the future. So actually, if it's not generalizable, if you've got 100% accuracy on the training set, so what? If it's no good predicting anything else, then it's completely useless. And it's a very common problem, and there's overfitting, and it means your model lacks that generalizability. In fact, if we look at this wider data, it seems that age may have played a much more important role in here. All of the Pencordians here are older in age, so maybe that we just had a bit of a blip here, that somebody who was younger who happened to be a Pencordian. Maybe this is a very small sample, so we don't. So let's look at this in a different way. Let's imagine this is our data. Where would you say is the true dividing line between the classes? So we've got yeses as ticks and crosses as no's. Yeah, around here. I would agree with you. I think it's around there. So that would be an example of a model that's been trained or fitted well. Okay, we can see as human beings, this side below 30 seems to be yeses, this side seems to be no's. And yes, there might be a few outliers, but generally speaking, if it's below 30, it tends to be a yes. If it's above 30, it tends to be a no. So that would be an example of a model that had been trained well. Here's an example of a model that's been overfitted. That's essentially what an overfitted model is doing, except your model will be in multi-dimensional space. It won't be in 2 dimensions, but let's not worry about that. Let's just think in 2 dimensions, because the principle's the same. But essentially, this model, it gets everything right in the training set, 100%. It gets everything absolutely right. So this is our training data. It's correctly classified all the yeses and all the no's. Perfect. We've got a 100% accurate model. Our job is done. Now let's have a look at some wider data. Now we've ended up creating a pattern, a line, fitting a line that is too specific to the training data, and actually isn't generalizable. It doesn't capture the fact that these maybe are just some outliers, and in fact the true dividing line is more like this. Okay, it's not generalizable enough. It's become too specific, and essentially that's what an overfitted model does. It's made the line too detailed. It's and gone around the corners, around the nuances of that data, when it's just a sample of data that it's seen. Now, as well as having overfitting, there is a problem known as underfitting. And as you might imagine, that's the opposite problem. So basically, overfitting is where you've overfitted, you've trained too much. Underfitting is where you haven't trained enough. Okay, this is an example, maybe this is the optimum fit here, separating out our data. So it's a slightly more complex relationship here, but that's perhaps where the line should be. But this is an example of an underfit. It just says anything less than 20 is yes, otherwise it's no. Well, it gets all this stuff wrong. It's not capturing the fact there's some sort of dynamic going on here where this value needs to, if it's very low or very high, would also result in a yes if it's if this value is very high. So we haven't trained it enough. Okay, now the good news is that underfitting is easier to spot, because if you've got an underfitted model, it's rubbish on the training set as well, because you haven't trained it enough. So it makes it really easy to spot, because you'll just have poor performance on the training, and that means you haven't trained it enough. So it does make it easier to find. Now, good practice, and you'll see this as we come through the course, is that you should overfit a model first and then take action to reduce the overfitting problem. And the reason you do that is you want to make sure your model has learned enough. So train it so it overfits initially. Then you know it's captured enough. It's just unfortunately it's captured too much. then gradually try to pare that back. And there's various interventions that you'll see later in the course of how you can avoid the problem of overfitting. You gradually then pare it back. It's much better to do that than to start with a model that's rubbish in the first place, because it hasn't learned enough. There's stuff that it hasn't found. There are patterns that it hasn't sorted out yet. So I keep talking about, whether models are good or whether they're rubbish. When we're developing a machine learning model, we need to know what it means to be good or to be rubbish. And we can use various metrics to assess the performance of our algorithm, the model that we're building. So we're going to have a quick look at some of the common basic ones, but you will see examples of other metrics throughout this module that you should also be using when you're judging the quality, particularly something known as a ROC curve, which we'll come on to next week. So let's start with accuracy. Accuracy is the one that is the most used, most reported measure of how good a machine learning algorithm is. It is, however, problematic. We'll come on to that. So when we're building a classifier, which is, remember, a machine learning model that's making a classification prediction, does it belong to one class or another? The three most commonly used metrics are accuracy, precision, and recall. Let's start with accuracy. So accuracy tells us the percentage of predictions that the model makes correctly in our well, it doesn't have to be the test set, but the training set, in the set of interest. Okay, so it's basically saying, how often am I right? So that means mathematically that accuracy is the total number I've got correct divided by the total number of predictions. So if I got them, if I made 10 predictions, they're all correct, I've got 100% accuracy. Okay. So here, what would you say is the accuracy of these results? So these are the actual colors of the circles. These text boxes are the predictions, and this is whether it was right or wrong. So what's the accuracy of these results?
60%.
Yeah, that's right. It got 6 out of 10 of them right. This one said it was green, that one said it was red, that one said it was red, etc. And these 4 it got wrong. So 60% accurate. There's also something called precision. So precision gives the percentage of correct predictions for the classification of interest out of the total number of times that classification was predicted, whether incorrectly or correctly. So that's like saying, when I say something is blue, how often am I right? Okay. So mathematically, that's the precision of a class is the number of true positives of that class, the number of times we said it was that class and we were correct, divided by that number, the number of times we said it was that class and it was correct, plus the number of times we said it was that class and it wasn't. And that's precision is really useful when your classes aren't evenly represented. So in this example here, we had 60% accuracy. What's the precision for classifying blue circles in the example?
67%.
Yeah, so let's have a look. So how many times did we say something was a blue circle and we got it right? Well, we didn't get that one right. We got that one right though, and we got that one right. So out of the so we've got 2 correct identifications, 2 true positives for a blue circle, and we divide that by those 2 plus the number of times we said something was blue and it isn't. So here we said that was blue and we were wrong. Okay, so that's a false positive for a blue. So essentially we got 2/3 of it right, 67%. So our precision is 67. Our precision for predicting blue circles is 67%. That will be different to our precision for predicting red circles or green circles. Whereas accuracy is just regardless of class. How many did I get right? Much like precision, recall is kind of the other side of the same coin. So recall is the percentage of correct predictions for the classification of interest out of the total number of examples that truly have that classification. So this is like saying, what percentage of blues did I correctly find? So precision is when I say blue, when I say it's blue, how often am I right? Recall says, how many of the blues did I find? It's slightly different. So this one, a recall of a class is the number of true positives for that class divided by the number of true positives for that class plus the number of false negatives for that class. The ones I said didn't belong to that class. I didn't pick them up, but they did actually belong to that class. So what's the recall for classifying green circles in this example? Yeah, so let's have a look. So how many times did I say something was green and I was correct? Well, this one I said was green and I was correct, and this one I said I was green and I was correct there. So I divide that by those two plus the number of greens that I missed, the number of ones that I said weren't green but actually they were. This one I missed, I said it was red, and this one I missed, I said it was red. So I got 2 out of 4 right, 50%. So my recall for green circles in this example is 50%. So let's think about what this means in reality for the kind of problems we might be looking at. Let's imagine that we're trying to build a classification model that determines whether someone has cancer or not. So high accuracy would mean that the model correctly diagnosed people as having or not having cancer most of the time. A high precision of cancer diagnoses would mean that most of the time, when it says someone has cancer, they do have cancer, and it's rarely telling someone they do have cancer when they don't. A high recall of cancer diagnoses would mean it's picking up most cases of cancer, and it's rarely saying someone doesn't have cancer when they do. And depending on your problem, it might be that one of those is weighted more importantly for your particular problem. So you can imagine in something like this, you'd probably want a higher precision of cancer diagnoses than, a higher recall than a higher precision. Because as horrible as it would be to accidentally tell someone they have cancer when they don't, that's likely going to be better than telling someone they don't have cancer when they do. Okay, so why might a high accuracy on its own be misleading?
If you classify everything as having the event of interest, then you'll be right in 100% of cases where that's true, but you'll also be wrong in 100% of cases where that's true.
Yeah, I sort of see what you're saying, but accuracy looks at all of the classes. So for all of the predictions I made, was I right or wrong? Basically, there is a fundamental problem with accuracy.
If you're predicting a rare event, you can be very accurate by never predicting it happens.
Yes, exactly that. So let's imagine that we are trying to predict the likelihood of someone being admitted to hospital in the next 7 days. And we've got our GP data and we've got all these features, and it's for tens of thousands of patients. And 1% of them are admitted to hospital in the next 7 days, and 99% of them aren't, which we would expect. We would expect something like that. We wouldn't expect to have half of them admitted to hospital in the next 7 days. That would be a ridiculous amount. But those are the patients that we're interested in. Okay, those that are going to, that's the ones we're trying to find. If you're not careful and you just base it on accuracy, you can end up very easily building a model that just says no one's admitted to hospital, because it would be right 99% of the time. The accuracy would be 99%. If you just had a rule that just said nobody gets admitted to hospital in the next 7 days, 99% of the time you would be right, but 1% of the time you would be wrong. And it's that 1% that you are interested in. And believe me, this is a very real problem that we see all the time. Every single year in HSMA, people forget this bit and they get really excited, and it's always lovely to see. And then we do laugh a little bit. We laugh with them though, not at them, because we've all been through it. Because they go, oh my god, I've got 95% accuracy, and we go, great, what's your precision and recall like? And then it turns out, yeah, it's just saying that never happens. That's why it's right 95% of the time. So be very careful about that, because usually the thing you're interested in predicting is a bad thing. And thankfully, in most cases, that bad thing compared to everything else is relatively rare. And so therefore, if you're just using accuracy, you're going to have a metric that says you are right most of the time, even if your predictor is rubbish, because it could be right 99% of the time if 99% of your data isn't of the data of interest. So be very, very careful about just using accuracy. And if nothing else, if you see a model reported and it's just got the accuracy, these are the kind of questions you need to be asking, because that may well be hiding a lot. Accuracy is a useful metric, but not on its own. You need to also understand it in terms of the round. Accuracy would be entirely useful without anything else if you had a 50-50 split in your data. Then that would be absolutely fine. But that's rarely going to be the case, and rarely should it be the case. So here, going back to this example where we had yeses and nos, the accuracy here is 93%. It gets 38 out of the 41 that are correctly classified by putting that dividing line down here. It's only those 3 that it gets wrong. It says they're yes when they're actually no. Precision for yeses is 88%. It's got but the precision for no's is 100%. Whenever it says no, it is no. And similarly, recall's kind of the other way around. Recall for yes is 100%, and the recall for no is 83%. So these results basically say this model, this line, is better at saying you do have this when you do than it is at picking up cases where you don't have it, because it picks up all of these, but it's missed a few no's by putting that line down there. Okay. With that in mind, let's get on to my favorite exercise of the HSMA program. This is, given what you've learned so far, you're going to put this into action, and you're thinking, but you haven't shown us any code yet, Dan. I know I haven't shown you any code yet. You don't need any code yet. We're just going to practice some of the basics. Okay, so we're going to play Dan's Desert Island DVDs. Okay, so what I want you to do, you're going to go into your groups, and you're going to try and solve this problem. So Dan, having grown weary of the human race, has decided to relocate to a remote desert island. And to keep himself occupied, he's decided to pack a DVD player and a number of DVDs. And we won't worry about how he's actually going to watch them. We'll just suspend our disbelief about that. So in an hour's time, I'm going to present you with a series of DVDs, and your task is to develop an algorithm that, by the time I present you with that algorithm will attempt to classify correctly whether I would take that DVD to a desert island or not. Now, I like a lot of films, but I've got to be a bit selective because I've only got so much space to pack all this. So I'm only going to take the films that I love the most. So over the next hour, to help you develop this algorithm in preparation for my list, you're going to be provided with some training data. That's going to be a list of films, along with whether or not I decided they should be, they make the cut for getting onto a desert island. So from this training data, you're going to decide which features that you're going to incorporate in your training. So there might be things like who's the director, what genre is it, what year did it come out, what decade did it come out, who's the leading actor, things like that. Okay. Now you're going to need to use, unless you've got an encyclopedic knowledge of movies, you're probably going to need to use IMDb and other online resources quite heavily for this. So I'd probably have a good couple of you in the group just pure researching the stuff to find out information. I'd suggest, you don't have to do it like this, but I would suggest to keep things simple, because this can spiral out of control if you're not careful. To keep it simple, just have Boolean features. So yes or no's. So is the director Steven Spielberg could be a feature. Was the film released in the 60s, etc. You could have numbers. You could have, for example, things like, what's the average review score, and the higher the score, the more likely it is. You could do that, but if you to keep it simple, I'd suggest you just have booleans. It's up to you. You can't have numbers though. They have to be either numbers or booleans. Now, what your algorithm should do, don't worry, I'll show you an example of this in a moment, is you should give a weight score to each feature, such that the score that's given to the feature, a score is basically given to that feature if that's true, or it could be if it's false, or you could use a negative score if you wanted to, but again, that's probably overcomplicating things. And then you basically add up the scores for the feature values for that film, and you have a threshold to say if the score goes above that number, then we'll say it does make it to the desert island. If it doesn't make it to that number, that threshold, then it doesn't. So let's show you an example, because that probably sounds more complex than it is. So let's say that I've decided these are my features. Was the film directed by Spielberg? Is the film from the 60s? And is the film a romantic comedy? Okay, let's imagine, probably need more features than this, but let's just imagine that I've chosen those as my features. And I've got two films here. This one was directed by Spielberg, wasn't a film from the 60s, is a romantic comedy. And film 2 is a no, yes, no. And here, this is my algorithm. This is what I've come up with. I've said, if a film for this feature, if that's a yes, if it is directed by Spielberg, then score 100 points. Is the film from the 60s? For this feature, you get 400 points if it's yes. So this one, I'm weighting highly. The presence of it being from the 60s, I've decided that's important. So I've given that a high score. Is the film a romantic comedy? I've said you get 50 points if it's a no. Okay, so I've weighted that maybe a romantic comedy, you get a score for it not being a romantic comedy, but not quite as much as the influence of being directed by Spielberg, and certainly not as much as this big weighted feature here. So then I can just add up a score for each one. So here I get 100 points because it was directed by Spielberg. It's not from the 60s, so I don't score anything there. And it is a romantic comedy, so I don't score anything there. So my total for this one is 100. And let's imagine I've decided my threshold is going to be 200 points. That one doesn't make the cut, according to my algorithm. In the second example, this film wasn't directed by Spielberg, so it doesn't score this 100 points. But it was from the 60s, and that scores big in my algorithm. That's a high weighting for this feature. So I get 400 points for that, and it's not a romantic comedy, which also scores me another 50 points here. So that scores 450. That exceeds my threshold, so I'm going to predict yes. So what you're going to do is basically come up with something like this. You're going to use the training set that I'm going to give you. I'm going to put it on Slack in a moment. I'll put it in the module 7 channel. You're going to use that training set to try and optimize your algorithm. You might want to consider carving out part of your training set as a validation set. That might be overcomplicating it, but feel free to do that. So you could try out and say, we won't look at that data for a moment. Let's try the algorithm on this. Seems to be working quite well on this set of films. Let's look at this set of films. Does this algorithm hold up? Is it getting most of them right? You should have a look at what your accuracy is, maybe your precision and recall as well, to monitor how well your algorithm that you're coming up with is training. And you can adjust your algorithms to try changing these scores, throw out features that don't seem to be important, bring in new features, change the threshold, do whatever you like, come up with something. But remember, be careful about overfitting. You don't want to do stuff that's too specific to the training data, which is all you're going to see for the next hour. But also be careful about underfitting. You don't want to not learn enough. Okay. So in an hour's time, I will then drop the test set, which will be another list of films, and it'll have, yes, I would take them to an island, no, I wouldn't. And you're going to have to apply the algorithm without changing it that you came up with just based on the training set, and see how good your algorithm is at predicting based on the scores you've given and the threshold. How many yeses and nos do you get correct? Okay, and we'll see who comes up with the best algorithm. Last year, so we ran this for the first time last year. I had absolutely no idea if this was going to work or not. and it did, and we got some really interesting information about my film tastes come out of this. And also somebody, I think, came up with something like, was about 80-90% accuracy and a really high precision and recall. So it can be done. So have a play around. Keep it as simple as possible initially, I would suggest, because this is quite a big task to do, and work as a group. And I would advise you, you might want to set people off to be looking at IMDb, looking stuff up, looking at potential features. Some people looking through the film list to see if they can see anything as human beings. But you're going to try doing this without the aid of a machine. Okay, I'm going to open up the rooms now. So it's 3 o'clock. So at 4 o'clock, I will post the test data. But for now, I'm going to open up the rooms, and in the module 7 channel, I'm going to post the training data. So this is the data you're going to use to try and come up with your algorithm. Okay. Any questions before I do that? No? Good. Okay. Let me stop sharing. Hi everyone. Okay, so welcome back. I hope you had fun with that. It was certainly entertaining going around and listening in to your algorithms and what you're developing. I noticed quite a few of you fell into my deliberate trap, where you may have noticed in the test set suddenly a lot of comedies popping up that weren't very present before. I definitely didn't deliberately hold those back to see if you'd fall into the trap of overfitting on a training set, but I did see some people getting some semi-decent results actually. So did anybody want to sort of share what they did? Did anybody get sort of pretty decent results out of the on the test set? Any good results?
I hope our team shouts up. We got 7 out of 8.
Oh wow! Okay, that was on the test set, yeah.
On the when we were comparing it to yours, yeah.
Yeah. Oh, okay. So anybody, was that accuracy? Sorry, or?
Well, we did it a bit kind of sporadically, really, because we kind of ran out of time to do any kind of proper testing. So we were just picking them out. But so our like categories that we did it based on. So we picked out Hitchcock, Kubrick, and Shyamalan as like key directors that popped up a lot. Good. We had sci-fi, mystery, or drama as like key genres. We picked out a few decades, so 80s, 90s, noughties, and 10s that came up a lot, but kind of gave them all different ratings based on how kind of prolific they were. And then the ratings, we gave a big score if it was over 7.4 on IMDb, but we gave it a minus score if it was under 6.
Okay.
So it might have been a film from a decade or a genre that you liked. Actually, everyone says it's terrible. So that kind of knocked it down a bit. But yeah, the only one that caught us out was Duel that we tested because it hit a lot of them, but we didn't have Spielberg as director. So that didn't give any kind of bonus points for that.
Duel is Spielberg, sorry.
Yeah, we didn't have him as one of our directors, so because he didn't really feature in any of the previous set. So
yeah, no, absolutely. Did anybody else find anything that was sort of powerful predictors? Any features you thought stood out?
We saw whether you were Tarantino or not. It was Tarantino as a director.
Yeah, anti-Tarantino specifically.
Yeah. We gave you a minus 37 if it was Tarantino.
Yeah. Quite pro Leslie Nielsen.
Yeah, Leslie Nielsen was a little hidden one in there.
Thanks for that.
Yeah, I noticed people's exclaiming, "Oh God, airplanes in there! That's completely mucked up our algorithm." So, yeah, that was quite interesting. I think when we did this last year, the group that got the highest rating concluded that basically the best predictors were: is it an 80s film starring robots? In which case you're probably good most of the time. Which is probably a pretty good description of my film tastes. But yeah, it's very interesting seeing a lot of you coming to similar kind of conclusions, picking up a lot of sci-fi in there. Some of the key directors that were clearly getting a lot of love or as in the case of Tarantino, seem to be a negative predictor. But hopefully the point of doing this exercise was to get you used to using the concepts of features, trying to find out information labels from feature data, and to experience firsthand the concept of overfitting, and in some cases underfitting. You may, I know a few groups, you could never get it performing well on the training set, and that's underfitting. And it was a tricky challenge that I gave you, because it's completely open-ended, and obviously on a lot of the data that you'll have, you will have a data set, and it'll be a case of choosing which of the features that you will include. And usually you kind of, with machine learning, you cast your net wide at the start and include everything, and then gradually sort of filter it down to see what really is needed in there, until you get to this. So you rarely have to sort of go out looking for things, as you did on this task. But no, some great stuff that I saw this afternoon. Some really interesting conclusions on that. So we'll stop there, and I hope you've enjoyed that this afternoon. So next week we'll go on to the next two sessions of AI next Tuesday. The morning we'll be talking about ethics in AI, a hugely important area, and I'll be showing you some quite disturbing examples of where the kind of stuff I'm going to be showing you can be used to wreck people's lives if you're not very careful. So we'll be talking a lot about that, and then in the afternoon we'll get hands-on with some Python stuff, and you'll get to do a relatively simple machine learning model using logistic regression, and we're going to be using the Titanic passenger data set, which is a commonly used data set in machine learning training, where we use real data from the passenger data from the Titanic, and whether they survived or died, and trying to predict, can we build a machine that will predict whether a patient is likely to survive or die the sinking of the Titanic. So we'll look at that next week, and then the following week we'll move into the wondrous world of neural networks, and then into how we can create fake data for if we want to be able to publish data, for example, that's completely fabricated. So lots to look forward to. Keep an eye out. Probably tomorrow I'll post up the instructions for next week, and hopefully I'll post up the solutions from earlier today, and the recording should go up tomorrow as well. Also, don't forget, those of you coming along to Elliot's recap session, second recap session will be tomorrow, recapping the module 1 content. And if you can make it, I'd strongly advise you come along to the 1 o'clock lunchtime showcase, or at least catch up on the recording if you can't, where Mike and Anna will be talking about the Samuel project, which is using the kind of stuff that we're now talking about, machine learning, to try and improve stroke care. It's a fascinating project. That's a big project, a big part of what we do within the Pencore team. So do look forward to that. Otherwise, I look forward to seeing you all next week. Please do keep practicing, have a look back over the stuff you did this morning, and please do share any models, etc., that you build. Post them up on Slack, and so other people can see and learn from them too. And continue to sort of post ideas over the next few months about in the ideas forum, where you can start to think about potential project ideas. Maybe today's session, this afternoon sessions, got some ideas flowing for potential machine learning applications as well. Okay, we'll stop there, and I look forward to seeing you all next week. Have fun, everyone.
Thanks.
Thanks, Dan.
Thank you.
Thanks, Dan.